Okay, fine. Yeah. So, is it other? Oh, sorry. Okay. Actually, right? Hey, minus. Hey, what all over the if I got to name either okay. Yeah.
Okay, so very good morning to all of you. So my previous speaker was telling about the quantum dot and some applications in particularly the photonics. Now I would like to present how those materials are grown. So it's like the growth of the materials, particularly I shall concentrate upon the growth of the nanowares, not exactly the quantum dots that Professor Kapoor has been telling. So I am Professor Pallav Banerjee from Indian Institute of Technology, Kharagpur. So this work is with some of my students and postdocs. So I gratefully acknowledge them. It's a kind of band gap engineering when you like to change the band gap of the material for different purposes. So in that sense, you know that silicon has certain limitations, right? And so you cannot use silicon for various applications, particularly the optoelectronic application, because of its indirect band gap, right? And you cannot change the band gap of silicon. It is fixed at 1.12 electron volt at room temperature. So now you can play with the materials, and different type of materials you can grow, like say aluminum gallium arsenide, the very important material, or gallium arsenide phosphide. These are all optoelectronic materials, and you are changing the group 3 elements, right? Aluminium, gallium, indium, they belongs to group 3 of the periodic table, and you are making alloy. So here also you are alloying in with the group 5 element, arsenic, phosphorus, antimony, right? So by this way that you can change the band gap of the material, and also you can have the quaternary system where you have changed both group 3 and group 5 sublattice. And this is possible when you use some 3,5 materials like arsenide, phosphide, or nitrides. Then you can have some different type of materials that you can grow. So one example is that say indium gallium arsenide is talking about. So gallium arsenide has a band gap of 1.43 electron volt. All these values are at room temperature, that means 300 K. And indium arsenide is 0.36 eV. And you can change by changing the concentration of, you can see indium and gallium concentration, you can change the band gap of this material. And so you can have your own material with a specific band gap. So that is important. Now, what happens that we have to take care of the lattice matching. That is important. You cannot grow any material over any material. Right? Okay. But the challenge is here that you have to integrate some photonic materials with the silicon microelectronics. Because silicon microelectronics, you cannot replace silicon in microelectronics or in VLSI technology. For optoelectronics, you cannot use silicon. Then to integrate the optoelectronics or photonics with the existing microelectronic system where it is very mature technology of silicon. So you have to have something like growing those materials over silicon, but the problem is the lattice constant. You can see that the lattice constant differs wide so far as the materials are concerned. So if you want to grow silicon, if you want to grow any of these materials over silicon, then large lattice mismatch will be there and the dislocations will come. And those dislocations will adversely affect your device. Obviously, you have to use different kind of epitaxial techniques like liquid phase epitaxy, Gepard phase epitaxy, or molecular epitaxy. It can be, say, metal organic chemical vapor deposition. So different epitaxial techniques we have to make use of for growing these materials. Okay, so I am not going inside all such epitaxial techniques, and so the problem that we have like to define is that the growth of 3,5 compound semiconductors on silicon substrates, it is the challenge. And because the challenge is dislocation-free growth of thinner planar materials of 3,5 semiconductors on silicon. So that is the thing, that how to overcome this thing, because it has large lattice mismatch, thermal coefficient mismatch is there, and deviation of the crystal structure between the substrate and grown layers. The silicon is cubic and diamond crystal structure, and then these materials are zinc blende structure. So the crystal structure deviation is also there. So to overcome these fundamental difficulties, growth of nanostructures such as quantum dots or nanowires can be beneficial. And due to the presence of facet edges and free surfaces, the nanostructures become strain relaxed and nearly defective. So that is the trick, that without going through the planar structure over the substrate, so whether we can grow the different type of nanostructures of say quantum dot or quantum wires or quantum wells over silicon. Thus, fabrication of semiconductor nanowire has become one of the most appealing characteristics as structures for the study of fundamental physics as well as the technological applications. So now there are several advantages of 3,5 nanowires. Say a vertical array of nanowires provide novel optical properties. One example he has given with respect to quantum dots. And advantageous for many applications, including nanolasers, LEDs, photovoltaic cells, and field emitters. For example, theoretical analysis indicates that vertical nanowire arrays have much lower reflectance compared to thin films. So due to the low reflectance, it is possible to develop highly efficient photovoltaic devices, say solar cells, etc. In high frequency regime, nanowires arrays have higher absorption than their thin film counterparts. In low frequency regime, nanowire arrays absorb less, but can be designed to approach the level of the film by changing the filling ratio. So if we can grow nanowires over silicon, so the possibilities widens up. Other novel functions like say direct conduction path for photo-generated carriers, then creation of natural wave guiding cavities, field emissions, etc. are also there. Now, these materials, indium gallium arsenide, we would like to grow. These have certain advantages over silicon. In fact, all 3,5s, arsenide, phosphide, even nitrides, have advantages over silicon. I have not included the nitrides because that is somehow different from these materials. So I am concentrating on the arsenide phosphide materials. So you can see that if we take the example of indium gallium arsenide by changing the molar fraction of indium to gallium ratio or like that, you can have this tunable band gap. So the band gap can be tuned from 880 nanometer to 3,300 nanometers. So wide spectrum of wavelength that you can have. Then high electronic mobility, tunable Schottky barrier height. Then you can have vertical field effect transistor, junction field effect transistor, photo detectors, tunnel diodes, and resistive switching devices. So that a particular material, just by changing the value of X, what is X? X is nothing but the flow of indium or gallium inside the growth epitaxial machines. So if you can change that thing, you can have this wide band gap regime, and then you can have different type of devices. So let us concentrate on a single in-gas nanowire. So we have used mostly the metal organic chemical vapor deposition system for growing these nanowires, and different type of structures we have grown, like say indium gallium arsenide nanowires on silicon, then indium phosphide nanowires on silicon, then indium phosphide silicon core cell nanowire structures. So different structures we have grown. So mostly those nanowires are grown by VLS mechanism, vapor, solid, liquid. There can be other mechanism also. I shall talk about that. That is VSS mechanism, vapor solid mechanism. So in this mechanism, this is very successful to describe the growth of elemental as well as binary 3-5 compound semiconductor nanowires. However, this gold catalyzed growth, because you need a catalysis, so that is the gold catalyzed growth of ternary alloy, particularly this indium gallium arsenide nanowire, is difficult to achieve since two different group 3 sublattices having different solubility, diffusivity, and incorporation kinetics are involved. So strong tapering of nanowires. So as you grow from the base towards the top, you will find that tapering has happened. So that is the problem with the gold catalyst. And it is because of these two sublattices exist here. Here you can see that you have started with a metal nanoparticle, say gold, then it has formed an alloy, and then the nucleation starts and it grows. Then we can see that this catalysis is here, and some tapering takes place. It can be single pronged, it can be multi-pronged. So one thing is that the diffusion of gold occurs into gallium. So tapered structure, then diffusion of gold, gallium into gold. So non-uniform distribution of the composition. So both things can happen. And then it induces defects. So poor electronic and optical properties you will find. Right. So another possibility is that the catalyst-free growth of in-gas nanowires. Here, in some of the cases, reports are there that heavily faulted microstructures are there. But whether we can overcome that, that thing also I shall try to present. So here we shall talk about this gallium self-catalysis growth. Not from the outside. I shall not use any gold or silver. Rather, the gold, the gallium we shall use for the growth of the material. Yeah. So I am not going into all such details. Here you can see that this is a MOCVD system. The flow rates have been given 45 SCCM in standard cubic centimeter per minute. This is trimethyl indium, trimethyl gallium. Those are the organometallics that we use, and arsine is used, which is 65 standard cubic centimeter per minute. Growth has at 500 degrees centigrade or 600 degrees centigrade, depending on whether you want single pronged or multi-pronged nanowires. So growth mechanism, I am not going into details of such things. Here you can see that the catalyst is here. So some tapering is also has taken place, and it gives a fairly good picture of what we have grown as indium gallium arsenide. So that is the growth is okay. It is a successful growth. It shows a single crystalline structure, and also the FFT pattern gives you the zinc blende structure. So reasonably good growth has taken place indeed. Also, what we have done, that distribution of indium and gallium along length of the nanowire that we have studied. And here also you can see position from the base to tip. So here, as we go from position 1, 2, 3, position 1, 2, 3 is okay. That means it is almost constant. It is the weight percent of gallium. Here it is the weight percent of gallium. It is weight percent of indium, the red one. But at this region from 3 to 4, you can see that it is somehow the indium concentration goes up and gallium concentration goes down. So obviously you can see that there's some uneven distribution of the materials has taken place. Uneven distribution. So here we can see that the silver is found advantageous over gold as catalyst. Silver is found advantageous over gold because compositional uniformity is disturbed whenever any element in the compound tends to diffuse into the liquid melt. So when at the beginning we talked about that gold and gold will diffuse, both gold will diffuse and gallium will diffuse to gold. So there was non-uniformity, but if you use silver, you will find that composition uniformity is not disturbed particularly. And gallium has a strong tendency to diffuse through gold. And so nanowires containing gallium as one of the constituent elements have a higher concentration at the bottom. As it grows, the gallium content reduces gradually. Such non-uniform composition of any of the elements makes the nanowires completely unsuitable for applications in single nanowire device. So here you can see that what happens in this case, that the away from the base, you can see that the indium concentration has goes up. So the performance of silver from this aspect is much more satisfying, as is observed in the present investigation. Okay, so now next thing that I would like to present here is that this growth of, you see, say VLS growth that we talked about, it has certain limitation. What is the limitation? Limitation is that incorporation of the catalyst into the nanowire often results in non-uniform distribution of the catalyst materials along the length of nanowire, leading to unpredictable electrical and optical properties. Thus, in route, single prone PSS growth can be an alternative approach. PSS, that means vapor solid solid. So here, what we have done, we have taken a piece of silicon substrate, P-type silicon 100. Then highly dense silver nanoparticles we have deposited over it. Then we have washed it for moderately dense silver nanoparticle. Density distribution we have taken care of by some means. And then particle assisted indium phosphide nanowires growth has taken place over this template. So we have used this template for the growth of indium phosphide nanowires. Yeah, but prior to growth, the substrates were pre-treated to have the silver nanoparticle on the surface. The various organic contaminants present in the wafer surfaces were cleaned on boiling in acetone and methanol. And then to etch the native SiO2, the silicon substrates were dipped in a chemical solution for 1 minute. So all such processes we have used and taken care of. And then you can see that the growth has taken place. So here, this is the growth, and you can see that here the nanoparticle is here itself. So not at the top. So from the position of the nanoparticle from the microscopy, you can guess whether it is VLSS or VSS. So this is a better approach so far as the silver particle catalyst is used. Here, the width of the nanowire was found to be 40 nanometer with a length of 600 nanometer, quite long. From the high resolution image here in figure B, you can see here in figure B. So here you can see that it has been found that the lattice spacing is 3.4 angstrom. It suggests that the nanowires were grown along 111 direction, and distinct spot in the set pattern. And you can see that it gives you the idea about the single crystalline growth. Single crystalline growth. And as no special care has been taken to cap the nanowires, partial oxidation has been found to occur from the cloudy ring in the SCAD pattern. From the TM image, no metal particle on the top of the nanowires is found. So that is important. It gives you an idea of the VSS growth of the nanowires using silver nanoparticle. So on the contrary, the contrast variation in the leading edge of the nanowires in figure A. So this is figure A. I am sorry that we have to go back again and again. So it indicates the presence of silver nanoparticles at the bottom of the wires. So the absence of the metal nanoparticle at the end of the nanowire suggests that growth process was controlled by vapor solid mechanism, where the precursors nucleate on the metal nanoparticle surface at the wafer stage itself. Okay, so these are the two techniques that I talked about. Next thing that I should talk about is the gallium nano droplets growth. This is a different kind of growth that the different metal catalyst we have not used. We have used gallium itself because the material is indium gallium arsenide. So we would like to use gallium itself. That is a self-catalysis growth. So growth of gallium nanodroplets on silicon substrate at different temperatures and growth durations to optimize the growth conditions to obtain spherical droplet. Once I have the spherical droplet on silicon substrate, then we shall use that gallium nanodroplets for the growth of nanolayers. So it's a two-stage thing. In the first stage, we have grown the gallium droplet on silicon, and then we have used that gallium droplet for the growth of nanolayers. So if you take a very quick survey of the literature, that nanowires are grown mostly by VLS techniques. A metal nanoparticle is required. It acts as the nucleation center. Novel metal like gold is commonly used, and diameter of the nanowire is determined by the size of the nanoparticle. However, serious drawbacks are there using gold nanoparticle, gold as catalyst. We have used, we have discussed earlier. Again, traces of gold is found in the side wall of the nanowire, and so the optical and electrical properties get changed apart from the top position. So here we have used these reactants like your trimethyl gallium, then different type of the arsine and phosphine, etc. So three different temperatures we have used for the growth of the nanodroplet. Let us consider that the samples were marked as S1, S2, S3. So only the temperature has been varied in this case, 450 degrees centigrade to 550 degree. Growth duration was 20 seconds. And we have not changed the flow rate of the gallium or the hydrogen. Hydrogen is the carrier gas in this case. And you can see that the density of the droplets increases at 500 degrees centigrade. Right? So at 450, it is 10 to the power 6. In 550, it is 10 to the power 7. But at 500, it is 10 to the power 10. So at a specific temperature, you can see that the density droplet increases. So why this density droplet increases? It is because of the fact that at this temperature, the 550 degrees centigrade, it is the temperature where the cracking efficiency of the trimethyl gallium, remember that is an organometallic element, organometallic compound. So at this temperature, the cracking is the highest. And so more and more gallium is found at the reaction site. That means at the reaction chamber, more and more gallium is available at a particular temperature. So here the successful deposition of gallium droplets were found on silicon 111. And effect of growth temperature, size, and droplet distribution were studied. If I can show you the droplet distribution in this case, you can see that the diameter, the size distribution of the droplet, you can see that the mean distribution is found to be 23.8 nanometer, and you can see that this clearly it is the Gaussian fit that we have made at the different diameters. You can see different diameters are achievable. It depends on the temperature and time that you can make some R&D for a particular size. And growth rate is very slow at low growth temperature, say 450 degrees. And that is why it is 5 into 10 to the power 6 was the density for the gallium droplets due to poor cracking efficiency of trimethyl gallium. However, at 550 degrees centigrade, smaller droplet coalesce into larger size. It is there, but it coalesces at that because at this temperature, you can see that the smaller droplet coalesce. And so this is before, and this is a partial coalesce. It is partial, and it is complete. Coalescence completed. So that is the thing that even at 550 degrees centigrade, the temperature is such that you can have the smaller droplets fall into larger size. So at 550 degrees centigrade, distribution of nanodroplet is uniform throughout the substrates with an average diameter of 27 nanometer and surface density somewhere between 10 to the power 9 to 10 to the power 10. An oxide layer is found to form at the outer surface of the droplets due to high reactivity of gallium with atmospheric oxygen. It is also there. You can see that from this view graph that this is the gallium core and the gallium oxides are there. At the outer surface, the gallium oxides are there. Okay. It is also found from your XPS spectra. And these nanodroplets now can be used for the in situ cell-catalyzed growth of gallium-based 3,5 semiconductor nanowires, as well as the synthesis of gallium oxide. Some in these days, you know that gallium oxide, a lot of work has been going on because this is very important material for high-power electronic devices. High-power electronic devices, gallium oxide. So people have been trying to synthesize gallium oxide. So once you have this gallium droplet, you can have you can use that droplet for the growth of the nanowires or the synthesis of gallium oxide as you like. So here, this is the last part of the talk, that it is a cell-catalyzed nanowire growth. So here what we have done, that growth temperature was taken at 500 degrees centigrade, obviously because we have earlier justified why this 500 degrees centigrade is the optimum temperature. And we have not changed the trimethyl gallium or hydrogen fluoride. We have kept as usual. Growth duration was 20 centigrade, 20 degrees, growth duration is 20 seconds. And if you see that, what is the lattice mismatch between silicon and indium gallium arsenide? For gallium arsenide, it is 4.1%. For indium arsenide, it is 11.4%. So that means, depending on the value of X, you can have 4.1 to 11.4%, somewhere between these two. So this type of a temperature time curve we have used for the gallium droplet deposition and then indium gallium arsenide nanowire growth. So this regime was for the nanowire growth. Here, up to this point, we have already discussed, that is the gallium droplet deposition for 20 seconds. Then 60 seconds, for 60 seconds, we shall grow the nanowires using that gallium droplet. So here you see that the growth temperature was changed. Growth temperature of the nanowire, not the droplet. Droplet were grown at 500 degrees centigrade. But this growth has been accomplished at different temperature. And here, since you know that indium is required, arsen is required because it is indium gallium arsenide. So flow is there, but we did not change the flow rates. The flow rates are kept constant for different temperatures. And duration also, it is 300 seconds. So 5 minutes we have used for the growth. Earlier, we have used 1 minute for the growth of gallium droplets. So here you can see that the morphologies of the nanowires at different temperatures. So you can see that this the diameter broadening is there. It is the bare substrate, silicon substrate. Then droplet of one of the constituent element of group 3, here the gallium. Then diameter increases at the length in case the particle size gets changed, as well as due to radial growth. So it changes. So this element analysis, from this thing you can have that indium gallium arsenide nanowires at 550 degrees centigrade. This is the element that has been investigated or found from the EDAX analysis. And from this result, you can see that this different spot, at different spot, we have taken this analysis. Not only at one single spot, we have taken this analysis at different spots, 1, 2, 3, and 4 spots we have taken. And from there, this 5:3 ratio that we have calculated, etc. That's simple one. And we have this 5:3 ratio of 5 we have taken because from the exact value of this indium and gallium, and 10 at the sample at S2, and that means 550 degrees centigrade, and then you can see at around 13. So actually what is happening that this with that at different positions, you can see that the 5:3 ratio is going to be changed. So morphologies of the grown nanowires for 550-degree growth with different 5:3 ratio. When the ratio is 5, when the ratio is 10, when the ratio is 13. So different type of grown has been taken place, you can see. And this is the bright field HRTM of a nanowire at different 5:3 ratio. So 5:3 ratio is you can see that the diameter is going to change essentially. The diameter is going to change. So this is the lattice fringe of the nanowires grown at 5, 10, and 13, 5:3 ratio. It is the inverse Fourier transform of image C. So very clearly you can see that the nanowires have been grown. And also the XPS analysis we have taken care of to understand the chemical. Okay, so here you can see that this particular 1:5:3 ratio of 3 we have used in this case. Not all the samples, it is a representative analysis at the grown at 550 degrees centigrade. So gallium 3D, indium 3D, and arsenic 3D spectra are available from the analysis. So what we have done in step 1, gallium droplets we have deposited over silicon at 500 degrees centigrade or 550 as the case may be. Then at step 2, indium gallium arsenide nanowires were grown at different temperatures, 5:3 ratio and growth durations over that droplet. So high flow precursor rates and long duration growth. You can see that very large length of the nanowires are found. Okay, and reduced growth duration and group 3 precursor flow rate, keeping this flux constant and growth temperature at 550 degrees centigrade. We can have this for high value of 5:3 ratio, VLS axial growth is dominant, and low 5:3 ratio, radial growth is significant. So depending on what you want, that you can make some changes in the parameters of the growth, and then you can have this radial growth or VLS axial growth, so that you can have. And composition varied along the length. So it is found that at low temperature and short duration, nanowires are vertically aligned. And base is indium rich, and gradually indium percentage decreases towards the T. So these are the findings from this study. So I acknowledge this IIT Kharagpur for funding this visit, and Department of Science and Technology, New Delhi, and for the experimental works, and also the organizers, particularly the program manager, Jerry. So thank you for your attention. So if you have any question, I shall be happy to interact. Yes.
Actually, we have did some work on the nanocarbon tube. So it's for the nanocarbon tube, it grows vertically to the substrate. But here I show you mentioned it will grow out slowly. Why is the difference?
No, it depends on the conditions of the growth. It depends on the conditions of the growth. It can be vertical also, it can be radial.
Okay, depending on the density.
Yes.
Okay. And how to control the diameter of the catalyst?
How to control
the diameter of the catalyst?
Diameter, yeah, or what?
Or the particle, where the wire goes out.
Yeah, so actually what happens, you see that first, if you want to grow this in situ, suppose then you have to use gallium droplets or indium droplets, right? So, so depending on the time of growth, the droplet size will be changing. So you have to make some R&D. You have to make some standard curve for your system. And once you can standardize your system, you can say that what type of diameter is available for what condition, for the type or the duration of the growth. Because in this case, I have shown you that the coalescence take place. So they merge together. So when they merge together, the site changes. Right. So you have to keep in mind whether they are merging, at what temperature they are merging. So so you must have standard curve for your system. It depends on system to system. It's a huge machine, epitaxial machine. So for a particular machine, and you can have your standard curves for this diameter, this your size, then growth rate. So also depends on the growth conditions. Yes, sir.
In the growth on the metal particles of the silicon,
Mhm.
you showed one example where the wires grow inclined and sometimes they grow vertical.
Mhm.
So what controls this? And more generally, what mechanism transfer the crystallographic structure of the substrate
Mhm.
through the non-epitaxial metal into the crystallographic wire? How is it communicated?
Which one, sir? Can you repeat the question?
Your substrate, silicon.
Yes. Suppose I have taken the silicon.
111, for example.
Yes.
Then you put a metal.
Yeah.
And this is not epitaxial.
No.
Okay. And then the wire grows with certain.
Sir, that
direction.
metal, sir, yeah, sir.
So how is the
Yeah. Actually,
information
that
transfer?
metal, actually, sir, the metal here acts as a gap.
I know, chemically, but
Yes.
crystallographically, how does it know to select the direction, for example?
Yeah. So actually, that is the thing that if you take 111 substrate, suppose we have taken 111 substrate, so growth will be on which direction? So that is important. So if you can have this gold catalyst or say silver catalyst there, so it is acting as a catalyst, and then it is going to be nucleated at that position. So it acts as a nucleation center. It acts as a nucleation center, and depending on the nucleation, the direction of the growth will be. So it's basically the nucleation. Okay. So thank you for your present hearing.
Okay, I would like to ask you this.
Present.
Yes. That's okay.
Sir. Can you please take this?
Let me go.
No, sir, no problem.
No, we have to do it. It should be done, right? Now present certificate of.
Thank you, sir. Thank you.
Okay, so now it's coffee break time, but before the coffee break, that's we meet in the after this, we meet again. We meet again at the conference at 11:35. Okay, 11:35.
Oh.
There you go.
Yes, Even look at the city. You can take the break after break. I will take the.
After the break, okay, we take it just before that.
Yeah, fine. Yeah, thank you. What is it? One, yeah, no, you can put on. You can copy.
Hi, guys. Hello?
I was not asked to send it, so maybe after lunch.
Hello, can you hear me? Hello?
Hello?
Hi, can you hear me?
Yeah, I can hear you.
Okay, I am Farida Slim. My talk, I guess, was supposed to be sometime in this session, but my flight, I actually can't, I just arrived now.
Okay. May I know your name?
Farida Slim.
Okay, Faridus Salim. Hello?
Yeah, so I'm actually not sure when I emailed even David Bishop, but I didn't get answer because I was not confused. I just actually arrived this morning because of my flight delay. I was not sure is the meeting in person or in online because they send me this link for Zoom.
Oh, okay. Actually, it's an offline meeting. So almost 3 people's already done their meeting.
Okay. So
Yeah.
now this is my question for my talk. This is online and in person and
Okay. I think you. Okay, give me a couple of minutes. I will check and let you know.
okay, let me actually ask a question. For today, it's gonna be harder for me to arrive, I guess. So I
Yes.
won't be able to do it in person today, but for tomorrow I can do it in person.
Okay, fine, no worries.
Can you
Okay.
check if I can do it? Do you see my talk and the agenda?
Yeah, here you are the third person here.
I
If you
am.
can- yeah.
I am Farida Slim. I don't know where it is exactly.
Yeah,
my
I understand.
I think my talk like 11 o'clock or something, but for
11 o'clock. No, your talk would be around 10:45 to 11:15.
okay. So actually, I joined by online, but I found someone else. So I don't know.
Yeah, I got it.
So
give me a
can
couple
you
of
check
minutes.
for me if I actually can even I can do it tomorrow morning, I guess it's probably easier for me. And
Okay.
I can join in person.
So still you are in the Zoom call, right?
I am what?
You are in the Zoom call, right? So you will continue in the meeting until finish today?
Yeah, until I can't continue until finish. I have another Zoom meeting with my university.
So finally, what
Yeah.
you are saying, you would like to give the meeting tomorrow, am I right?
Yes, I actually would like to give my talk tomorrow, and I hope if it's still in person.
Okay, may I know at what time you want to give the meeting?
Tomorrow. That's a good question. So tell me what's the option? I can give it today after the break online if this is better for the schedule.
Okay. You just inform them. I will talk to my.
Okay, so that's the two options for me. I can give it today after the break.
Yeah, I understand.
Right now after the break online because I won't have time to come.
Okay.
Or I can do it tomorrow. Whatever option, guys.
Okay. Just 1 minute. Yeah.
Okay. For tomorrow, I can do it in person or online, wherever actually work. Hello? Hello?
we can hear you. Hi.
Hi. Hi, did you figure out?
Yeah, hi, can you share your screen?
Yeah, hi, did you figure out for me if I can tomorrow, if it's available for me to do it or not? Or
without any notification, I can see if it is internet is disconnected. Then how can we work? Okay, fine.
hi, can you?
Just show number.
Is it possible that we can present today? Now or maybe something later? Hello.
Hello?
Yeah.
Yeah, so did you figure out for me if I can give my talk tomorrow instead of today or what?
Yeah, I just wanted to ask, is it possible for you to do the presentation?
Excuse me, I can't hear well.
Yeah, can you hear me now?
Hello?
Can you hear me now?
Yeah, not really. Let me try if the voice. Yeah, can you speak now? I may hear better.
Yeah, I just wanted to ask, would it be possible that you can give the presentation today?
No,
Maybe
not
now
the
or
Google
sometime later. Is it possible?
Yeah, I think I can. Tomorrow is all online, or you have online and person option?
Sorry. At least before lunch at least go. తర్వాత ఉండరు. Okay. అదే అప్పుడు క్లారిటీ లేకుండా కాన్ఫరెన్స్ గురించి తర్వాత క్లారిటీ వచ్చింది కదా, రెండు కాన్ఫరెన్స్. Hello.
Hello?
Yeah, sorry. Victor here, I'm the organizer. So would you
Yeah.
like to present now or would you like to present tomorrow?
Can you repeat? I can't hear you well.
So being a virtual participant, I request you to present tomorrow because today we have scheduled all the in-person participants. So
Okay.
you are at the hotel. If you can go to conference room, then we can schedule your presentation directly.
Okay, but I'm not actually. I'm in different hotel.
Oh, okay. So can you join?
but
Can you present tomorrow virtually?
Yeah, I can present tomorrow. What time you want me to present?
I'll schedule and I'll schedule it, okay?
Okay. I think is there option? Okay. Is gonna be online or in person?
Yes, both are there. Like first day will be in person, second day will be virtual.
So tomorrow is gonna be both online or in person?
Yes, completely online.
Oh, all online. So I have to
Yes.
present you online tomorrow.
Yes.
Okay. So yeah. So please let me know at what time actually.
I'll send you mail, okay?
If I
Can you
can
just-
do it sometime tomorrow morning, I guess it'll be good.
Yeah, I'll do that.
Unfortunately,
I'll do that, okay? Can you just stop sharing your screen, please?
I stop sharing.
Yeah, stop sharing.
I'm not sharing.
Okay, then fine. Please wait,
It's-
okay?
It's not me. I'm sharing. I'm just.
Yeah, please wait.
Okay.
Thank you.
Better like this. Okay, the first topic will be the bovine respiratory disease. What it is. Wait. It's working, yeah. Okay. So bovine respiratory disease is a disease which is caused by different bacteria and viruses. And I may say that we use these antimicrobial peptides, which are worldwide used for treatment of this kind of diseases, because they allow us to work in different range of acting for this bacteria, and we avoid this resistance from both bacteria and from viruses. So we selected some different antimicrobial peptides, and we prepared this. I don't know why it is not working, but this is a nanoparticle containing only this antimicrobial peptide. So we mix all of these antimicrobial peptides, which are linked to scaffold protein, in order to be bigger and to be easy to manage it. And for our practices and for our first steps, we use the green fluorescent protein, which is very, very used for this. So the objective of the research line was to set up an evaluated detection of protein-only nanoparticles containing both antimicrobial peptides using liposomes and micelles to overcome this bovine mucus barrier for the drug delivery in that case. So as I said, we use this GFPH6 as scaffold protein, and then we selected two different peptides, which are the antimicrobial peptides that we selected from our library. Once we selected it, and once we target which were the best one, the best candidates, we try to do a kind of experiment in where we decide which is the best buffer to have these proteins, and that's why we perform this microdialysis, in which we use different buffers approved by FDA. In that case, we finally moved to the one which is with 100% of solubility, because it was acetic acid at 0.01%, which is low pH, but it's the best worker for this for our proteins. What do we have in the mucous barrier of the cows? We have different bacteria, which are the causing of this pathogenic of this disease, which is most of it is Pasteurella multocida, Mannheimia hemolytica, and Pseudomonas aeruginosa are the mix of the top bacteria causing this disease. And we added, just in purpose of our experimentation, Escherichia coli, which is very, very easy to use for our experiment. So once we checked for all of the main bacteria that are involved in our disease, we checked the mortality, and as we can see in page 4, 5, and 6, we have the biggest range of mortality for this bacteria when we're using it. Just to remind you, when we are using acetic acid buffer, we are in between 4 and 5 of range of pH. Okay, in our case. So I move, as I said, another big problem that we find in the mucous barrier of the cows is that this is the mucous system, I may say, but here there are a lot of proteases. So if we deliver the naked structure of our protein, it will be just dissolved by these proteases. So it will have no effect to our target, which are the lungs of the cows. So that's why we thought about a first system, which is using liposomes to cover a little bit these proteins that we prepared. Just to introduce you to the world of liposomes, we began with multilamellar vesicles. When we extrude them, we get these large unilamellar vesicles, which are around 100 nanometers of size. It is performed by this kind of structure, which can allow us to separate us the liposomes and the free protein, which is not charged inside of the liposome. Okay, so if we move, we have different kind of liposomes that we perform. The first type is just 100% of phosphatidylcholine coming from egg. And we charge it with, we load it with GFP for one side, and we also load it with first of our antimicrobial peptides, which we'll go further now from HDP1 and HDP2 as the second one. And we perform exactly the same experiment, but using a different composition, in which instead of using 100% of phosphatidylcholine, we mixed phosphatidylcholine with 30% of cholesterol, and in the reverse phase, we used 40% of phosphatidylcholine and 60% of cholesterol, just to check if there were differences on. So what we got here in the first experiment, using reducing our liposomes, we effectively checked that the size of the liposomes was the expected one, because after the extrusion with a filter of 100 nanometers, we got liposomes of around 82 nanometers, which is the expected size of these molecules. And the big problem was when we performed the first in vitro experiments, mixing these liposomes with cow mucus, where we got known surviving protein. So that was a big problem for us, because after all of the experiments, it was not possible to protect our proteins. So what else we performed? Something that was very important also, when we mixed with cholesterol, we could see that it was there was a little bit of more protection, and it was time depending all the time, because at the beginning it was 100% of our protein safe, and by the time it is just in minutes, okay, it is 5 minutes because it was over here, but it's not appearing. But by the time it's lowering the concentration of our protein, so it's being again because of the activity of the proteases in the mucus. So as this system was not currently working, that's okay. We checked it; it was not working. We moved to another type of protection, which are the micelles. Micelles, we produced it in two different types: the electrostatic interaction with our protein and covalent binding to our protein. It has different endings, so it has different interaction between the micelle and our protein. It is produced with this polymer called plurionic F127, and we mix with different concentration of plurionic and percentage of our protein to prepare our micelles. In the first experiment, what we saw that this is the biggest difference between the liposomes and the micelles, that after 1 hour of interaction, it is very low, but it's appearing that there was surviving of our protein. So it means that our protein was still in its native structure, and it was active towards these bacteria that we talked before. Yeah. Once we check the structure of these micelles after between the time, between the temperature, we could see that at a different range of temperature, this is the first one of our antimicrobial peptides. This is the second one. This is not correct. This should be a 2, but it's along the temperature. It's getting exactly the same size. So that's very important, because we can keep all along the different. We don't need to be cooled to keep this working well. Okay. What else we have? And finally, these are the assays, the in vitro assays. In the first one, we could see that the different range of pH when we mix it. That's against what we said in the beginning. The best pH to work for against this bacteria was at high pH, at pH of 8 or 9. Remember that the biggest problem was that we have the best working of our proteins at pH of 4 and 5. So it's been against. But when we mix it all together and we perform our in vitro micelles mixed with the cow mucus, we got that the conjugated one, it means the covalent one, were super. There was a big effective here, but the one which is not appearing, which are the conjugated at 15 micromolar, which means micromolar of our protein, was the best effective, was non-survival after 24 hours of incubation. No survival of this bacteria. So that means that we got the protein one, the system that was working, and now currently we are performing our in vivo assays with different cows. So to demonstrate that our system was performed correctly for delivering intranasal our protein. The second line of my research, it will be now shorter for you. It was the recombinant vaccines in collaboration with the University of Sao Paulo. We released last year a review talking about the perspective of this recombinant vaccines in 2022, 2023, which are going to be the most interesting fields of research. And in this review, we talk about the different ways to perform our vaccines and to deliver it to the system. But the most interesting one was using this scaffold protein, as we talked before, with a peptide linker and our antigen against our target in our disease in that case. Okay. And here there is another paper which is going to be released very, very soon, which I cannot talk a little bit much more than this, but once we were performing our experiments towards this review article, we discovered by accident or by chance, I can say, that when we mix different molecules during the purification of the proteins, there was a high performance of the purification system. So it will be released very, very soon. It is a substance that just change the conformation of our protein and get the better approach to the nickel column, which is the one it's more common to use while purification proteins. And finally, this is the last research line that we just began in December 2022. It's 2022, could be 2023. It's in the really beginning. We are just starting this in collaboration with this University of Western Australia, and I have no results yet of this system, but it will approach a little bit of precision medicine, which is now in the top level of the medicine, which will use cells from tumors in the case of somebody who just got cancer or something like this. So using that cells will produce the kind of solution for targeting and delivering the treatment to the cells. So I would like to acknowledge my research group from Barcelona, also from the collaborations, also to this to the committee of the Congress to invite me to be here, and I would also acknowledge everybody of you who took attention, and thank you very much. I could please hear.
So, it's open for questions. Please.
Regarding the third part, the precision for cancer treatment, so you would be, so like there is CRISPR that you can just.
It is different to CRISPR.
Okay.
It is a different system. It is more related to what I'm doing. I cannot talk too much about this, but it is just a new system which involves using own cells to deliver our drug to this patient.
Okay. So, but how would you make it precise? Like even with chemotherapy, they say that you are like you use radiation, but then healthy cells could also get killed when you're trying to.
The percentage that in our initial steps is that 95% of our target cells are straight going to kill, not the rest.
Okay.
One question?
Oh, yeah. Okay.
Okay, thank you for your talk. And here's a presentation.
Okay. Thank you very much. Okay, thank you.
Our next speaker is Florida Stedman from you from sorry, Florida from Germany. this.
Thank you for your kind introduction.
Professor Pepper, Dr. Pepper works in the Institute of Machine Design and Tribology, Leibniz University, Hanover. As a postdoc, his research in material engineering, manufacturing engineering, and tribology. Please.
Yeah, thank you for your kind introduction. This work was done in Hanover at the Institute for Machine Design and Tribology, together with Professor Boll and other institutes involved. And we investigate graphene as dry lubricant and also as grease additive. Recently we have been having some very good results on real bearings and are interested to have deeper insights. So we extended our studies. The first thing is that we apply the graphene platelets on real bearings with this size used, for example, in robot arms moving in oscillation motion. And we have to find a process to apply this graphene on bearings and tested them in a so-called FE8 bearing test rig. And with the very good results, we want to understand the mechanism and extended our studies to tribometer tests. The application for dry lubricants can be found, for example, in space or very hot conditions, or for machine elements that need to move from time to time, that they can still stand for many years or weeks, months. But when you need it, it have to move. So there, something like graphene is very interesting. We have also other projects investigating molybdenum oxide for this purpose, but the graphene is a little bit better in friction conditions. As you see here, this robot arm, that is a project where we also investigate greases, but we think that graphene can work as well. You can have under very high oscillating frequencies, also high temperatures. There the graphene can help. You can use it also in challenging conditions, like a little bit like vacuum or high temperatures. And we investigated different kind of so-called graphene platelets. I will explain as well. First to this graphene. Normally, it is like from the graphene, a single layer, it's shown here. It's having a very high tensile strength. It conducts heat very effectively. It improves also when we put it to grease, the conductivity very good. It's a problem for e-motive that you have inductive currents. So you damage your bearings, and by putting graphene inside the grease, you can have much better conditions, and the bearings can live much longer. There are also some studies putting on ionic liquids in, but in our case, we have very good results also with this graphene. And it's nearly transparent. And one very good thing is that the graphene passivates our steel surface. That means when we remove all the oil from our bearings, apply graphene platelets on, it is not oxidized anymore. We can store it for many weeks or months. And here's a little bit to explain the graphene. You can make from graphene this buckyballs of fluorine, nanotubes, or also something like graphite. Of course, it is as a single layer extremely thin in the nanometer range, or 0.3 nanometers. And in our application, we use platelets. That means it is several layers of graphene, like a very thin sheet of graphite. But the aspect is the nanometer high, like 2 or 3 nanometers up to 15 in our investigations. And
like a carpet. It's a few micrometers wide. Here's a little bit shown how you can make it. It's like on the mechanical way, some unzipping of nanotubes or by CVD processes. Also this growth on silicon carbide or some chemical exfoliation. And what our graphene is produced is in this way. It's relatively cheap. We can, our supplier, use graphite, and it's sheared between plates, this photostator shearing units, and we achieve this graphene platelets. So it's a mixture between graphene and graphite. It can be produced cheap, so beneficial to apply it to grease or for bearings where you not need real graphene single layer sheets. You can use this graphene to reinforce epoxy resins shown in this helmet to make it very strong, and also foldable devices. You can fold it and it's conductive, and also put it into MEMS to as a conductive layer. So there's a lot of work done. And also in the tribology, that's the study of moving surfaces in motion where you want to reduce wear and friction. And a lot of work is done recently on the nanoscale. Here's a little bit from the literature. That means very low forces. Typically, we use silicon or silicon carbide as substrate, or also somebody carbon coatings, low forces, low loads, but no real tribological application on machine elements. Little bit stuff was done on the micro scale. That means loads in the range up to a few Newton. And Radi to find something where they investigated steel. That's where we step in, use these bearings. It's an angular contact ball bearing with not so easy conditions for our grease, or in this case trial application, because we have not only a rolling of the ball here, there's also a spinning motion, because there's some differences in the radius. So it's not a real rolling. You have a spinning motion with slip and increased wear when we don't take good care for our lubricant. This is a Strada curve showing that under start and stop conditions, like oscillating motions in a robot arm, the very low speed regime is very important in terms of our additive and the surface properties of our bearings. So that we have to regard this for our tri lubricant as well. The processing is done that we used dimethylformamide to bond our graphene on the steel surface. We mix the graphene with this DMF and then applied it by dapping the bearings in this lubricant. Afterwards, we put it to an oven, 120 degrees for a few minutes, and afterwards in our test rig and inspected the bearings. So this is the graphene agglomerated on the bearing after the oven, after the heating. This is a picture of the test rig. We have a motor performing an oscillating motion, 48 degrees, like this, the whole time. We have our test bearings inside here. We load it. We have an Hertzian pressure of 1.5 gigapascal. That is a typical load for bearings, a little bit higher. We mostly have like 1 gigapascal. It can be used up to 2 gigapascal, the pressure. So it's a, when we think just like a tri lubricant, a harsh condition. And a typical test condition like we can find also in wind turbines. This is a test rig in our lab. And interesting, our first test, this is a standard bearing. So as said, we have a oscillating motion. This is the pivoting angle, plus minus 24 degrees. And this is the frictional torque that we monitor. And we can see for the grease lubricated bearing, the frictional torque. In our first test with graphene platelets, we could reduce the frictional torque significantly. We did some more investigations to improve our process and apply other kind of graphene platelets. And you can see that we achieved very good low frictional torque in our tests. So we had to think how this could happen. Here's just a benchmark to compare different kinds of graphene platelets. Thicker one, it didn't reduce so much. This one in the medium range of the thickness of 6 to 8 nanometers was the best. And this one performs still good, comparable to graphite nanoparticles. And here's a SEM image of such graphene platelets. Yeah, so we investigated the bearings on a microscope. This is just a test after 3 hours for an unlubricated bearing. It failed totally. And our other bearings we tested for 1.3 million test cycles. That's more than 3 days. And you can see here on the raceway, it's still intact, the surface. We have some black layer on the surface. And on the reversal points, a very compressed, thin graphene layer, which seems to be very beneficial for our bearing application. This is a SEM image. Here's a reversal point of the raceway of our ball. You can see that the bearing is still intact. The ball itself, due to the spinning motion, we have here also there are some stripes on the surface with very thin graphene on the surface. We also did some nano indentation tests showing that the hardness is not so high, like below 1 gigapascal. And the idea is that the ball under this reciprocating motion forms a thin but very beneficial coat on our bearing, similar like a DLC coat. And to prove this, we performed some tribometer tests. That means this millitribometer was equipped with a rolling ball to make the same process to achieve this thin layer, and afterwards measure the friction in a sliding test. So this was our roller. We do a pre-rolling process. Yeah. Some parameters that we tested, not so interesting now. And we measured after the pre-rolling the friction for the different kind of graphene platelets shown here. And I want to show some details on. A fullerene didn't work so good. It's like balls. It was removed out of the contact. The graphene worked quite good. And we can see this is with the pre-rolling process, without pre-rolling, that in some cases, like for the 6 to 8 nanometer graphene, we achieve a much lower friction of our surface due to this compacted graphene layer. So this is a friction coefficient approximately 0.1, which is good for our tribological system. It's comparable to a oil or grease application. So pre-rolling helps us to achieve beneficial layer for our graphene platelets, especially the 6 to 8 nanometer thick platelets. Here's to visualize the effect. Without pre-rolling on our surface, the graphene is pressed out of the contact, and we achieve, it's hard to see here, some wear on the surface. And in case of this graphene, we have a thin layer on the surface. It's also shown here. we have zero wear. It's like a thin trouble film on the surface, which is quite smooth. There we did some nano-indentational tests as well to investigate the mechanical properties of this film. It's shown here. So the hardness is not so great. It was 0.6 gigapascal, comparable to an epoxy resin when it's hardened. But as it's very smooth, it seems to be beneficial for the tribal contact of the ball sliding or rolling. The steel it's shown here, it's much harder, of course, but the surface is not as smooth and suffers to wear after some time. We also investigated the wear on the ball for different graphene platelet thickness, shown here. That in case this is pre-rolling, you have very low wear on the counterpart on the steel ball. This is without pre-rolling. There we have much higher wear typically. So we think that when we have very thin, like 2 to 3 nanometer platelets, it's not so effective to protect the surface as the thicker graphene. The best one was afterwards this with a 6 to 8 nanometer thickness. And when it's very thick, it depends. In some cases, we have good properties, but in the bearing test rig, it was not as good as this 6 to 8 nanometer thick platelets. So in any case, we could prove the application of graphene platelets for machine elements like the bearings. We can apply it. At least it can cut the frictional torque to half. And we have now first steps to understand the mechanism. We still try to get some more funding to stay in this research. Currently, there were also some studies in Egypt. They also put graphene platelets into Greece and did some investigations. Luckily, this colleague will start next month in my team, so the competence is coming also to Hanover, and I think we will have some more insight in this application in the near future. So, thank you for your attention.
Question? What was the binder?
It is some acid that helps to bond the graphene to the steel, but it's a low bondage. We found in literature from Japan that they could bond this graphene to steel with this DMF, something like an formic acid.
The effect of loading concentration with your bearing. What was the percentage of the using loading and using concentration in the solution? Yeah, the solution that you need to form the layer of the bearing. What percentage
of graphene? I think it was like 5% of graphene is this DMF, and then we could dip it good inside, like the mass percentage.
My previous study discovered that at high concentration, we have a lot of, you have a solid lubricant in your polymer, and when it's increased, we have what we call agglomeration, and it does the bonding will not be strong, and the sliding you are looking for. But at 3%, not in 1% is
Yeah, here it is a thing that it's just as liquid, it's evaporating. But when I put the graphene to oil, we also have studies with PRO6 oil or also with put it into grease. Then we use much lower concentrations. like 0.1 to 1%. And we also have to regard that the volume is very different when I use very light, the graphene with which is very thin. The volume is different than if I use the fullerene or as if I use thick graphene.
And what was the effect of that on your friction?
Yeah, could prove that in any way when the friction is reduced, also the wear is of course reduced, in this case.
Thank you.
Please. I do also have questions. What's the idea about the recovery speed? Because for solid lubricant, when it's friction and wear, it will be move out. So the recovery is very important. What is the idea about graphene? It's possible recovery during the procedure.
I think as we tested like at 5 Hertz for 3 days, that's 1.3 moving cycles, that it will stay for a very long time. There's also some studies, they use graphite in Karlsruhe at the KIT. They have some to spray it inside mixed with ethanol. They think the ethanol will evaporate very fast. But this way it's no real dry lubricant. It's a little bit, Martin Dienwiebel makes it also interesting, but I'm not sure if it's really dry lubricant, but they mix it then with ethanol, spray inside. That's a possibility, of course. But this is intended to stay for a long time. And if you have something like a door that needs to open automatically, but like a high security door 2 or 3 times a year, then we can be sure that it will work, because the graphene helps that it's not oxidizing and we have a low friction.
So you're using multi-layers of graphene between 10 and 100, I think. And the nice thing about graphene is that you can control it in principle at the monolayer level. Is there an optimum thickness to get your lubrication?
Yeah, we saw that for our application, it is like 6 to 8 nanometer thickness. And we tried what we could get in Germany easily. It was supplied by Aeolitech. They have some like 2 to 3 nanometers, 6 to 8, 11 to 15, and some undefined. So we took the 3 defined one, and that worked good. And it's payable, like a big portion for €100 for the Greece manufacturer. It's still a little bit too expensive, but I think the prices will drop as it dropped the last 10 years drastically. We started like 10 years ago to mix some fullerene to epoxy, and that the prices was you get like a few milligrams for hundreds of euros, and you can get a big bottle.
Any question? So, thank you for your talk.
Yeah.
And I will study the food later. Our next speaker is Dr. Han. Dr. Han from University of Chinese Malaysia. He received his Master of Science degree in Natural Science from University of Cambridge, United Kingdom, in 2021. Specializing in physics, he is currently pursuing a PhD in physics degree in the University of Science Malaysia, Penang, Malaysia, one of the fast-tracking programs. Please.
Yeah, I think this is fine. So thank you everyone for the chance to present. So my name is missing a surname. So it's actually, so no, it's okay because that's what happens on the booklets, but you can call me Joseph. My surname is pronounced as oui, as in the French word for yes, oui. So I'm here to present a paper that I've published in cooperation with my supervisor and also some research members, as listed here. So I'm here to present the numerical assessment of horizontal scanning LiDAR performance via comparative study method. So this is my first PhD publication and quite excited about it. And hopefully with this, I can hopefully finish my PhD studies in Penang. So to give you a background on why we conducted this study. So I'm sure everyone is concerned about your health, and especially in countries like Malaysia and in Southeast Asia, in countries with high industrial activities, haze is a problem. Aerosols are present in haze, and that is also a big problem. So in Malaysia, for example, the major sources of aerosols in air pollution episodes can be listed as transboundary haze, biomass burning, and motor vehicle emissions. And the problems that it creates are health-related. For example, aerosols have been shown to induce asthma, this is weird. Let me see if I can hide this bar. Hide video. Aha. Yes, great. The problem is when your slide that goes down to the very bottom. So let me start again. So aerosols have been shown in studies to induce health-related problems like asthma, stroke, and heart disease. These are the more common ones. And they can also cause pregnancy complications. So obviously aerosols are not good for us. Right, I'm back in my slide. So how can we monitor aerosols? So there are several ways. The most basic way, or the most common way that we use in Malaysia, is to operate air quality monitoring stations. So these stations use direct sampling techniques. For example, they have flowing equipments that absorb air, and then you carry out analysis like gravimetric techniques. So this is a point measurement, meaning that it only samples the air in the direct proximity of the station. So what that implies is this measurement is not very accurate when you move further and further away from the station. And the point of monitoring aerosols is that hopefully, instead of just looking at one point, you can map out the distribution of aerosols. And that gives you more information on how you can tackle, for example, sources of these aerosols or regions that you need to take notice of where people's health may be at risk. So an alternative to that would be to try to use satellite monitoring, for example, MODIS. And this gives you aerosol optical depth data. So satellites can, obviously, they have a bigger range, but they have poor temporal resolutions. The best you can get, the best data that you can get is down to a day. You can't get it by hours. You can't get it by minutes. And that doesn't really help you when you want to monitor the air pollution, for example, from morning to afternoon. So we propose that LiDAR, which is a short name for light detection and ranging, would be a better alternative to using air quality monitoring stations or satellite monitoring techniques. But because this is an optical remote sensing technique, you aren't actually sampling the aerosols. You are retrieving characteristics of it in the extinction and backscattering coefficients. And from studies in places like China, they have shown that you can have large scanning areas covered in real time, which means you can get very high spatial and temporal resolutions of the optical properties of aerosols in that area. However, there is no foolproof way. There are benefits and challenges to using LiDAR. Okay, so I'll read it out to you. So the benefits is you can have different application-specific LiDARs. For example, you have Doppler LiDARs that operate to measure wind speeds. You can have high-resolution LiDARs, or you can have differential absorption LiDARs, which can detect trace gases, or you can have the most basic elastic backscatter LiDAR that just samples aerosols in general. And this gives rise to a more efficient way of carrying out air pollution monitoring. However, in order to procure a LiDAR system, you need a lot of money and you need a lot of specialization, because these systems are very sophisticated and expensive. Without funding, it is almost impossible to get a cheap LiDAR for air pollution monitoring. Therefore, in order to cut costs and to save resources, some researchers have started to resort to building their own LiDARs. However, the problem with that is, in order to have a workable self-developed LiDAR, you need a cost-effective design, and this LiDAR itself must have a comparable performance to conventional setups that you can get on the market. Otherwise, there's no real use of having a cheap LiDAR that doesn't work. And the caveat to that is you don't know how your LiDAR would perform until you carry out field tests, because LiDARs may have different performances according to variations in region or climate. Therefore, the most basic way, the foolproof way that researchers with access to LiDARs use is you compare experimental data to what you would expect from the usual LiDAR equations. And then if it matches or there's no real problems, then you can say that this LiDAR setup is okay. However, assembling prototypes requires a lot of resources and expenditure, and this is even before design flaws can be detected and improved. So the aim of our study was to present this numerical assessment of horizontal scanning LiDAR performance using a comparative study method. So this is an alternative that we have proposed, and the advantages of this alternative method is you can evaluate LiDAR performance without physically assembling the unit. This gives you a preliminary idea of what you should be changing before you actually move forward in your development phase, which helps you save precious resources and time. And we can use a hypothetical setup to demonstrate this. So in this hypothetical LiDAR setup, we use at least two example LiDARs in the literature. And here we have a Sheena LiDAR, which is a LiDAR developed by a Japanese researcher, and a VAST LiDAR, which is a LiDAR that is used in Vietnam. And by comparing our hypothetical setup to these two LiDARs, we can identify any design flaws and then look for improvements to them. So the study objectives are as follows. First, you need to develop an algorithm to simulate your setup in a modeled atmosphere. This is because there are no real ways to model the atmosphere for our applications, which is to do a horizontal scanning LiDAR, which is a LiDAR that scans parallel or near parallel to the surface. And in developing this algorithm, you can do some optimization first. Then, because we have regional and climate variations, it is important to obtain real meteorological data as input parameters to this simulation program in order to, for example, simulate the general atmosphere and also background solar illumination. In order to get your LiDAR performance indicators, we need to calculate the signal to noise ratio and the range corrected signal profiles. And we chose a horizontal detection range of 1 kilometer. I'll explain this more later. Lastly, we need to conduct this comparative study method by considering the effects of transmitter and optical components on the performance of this LiDAR, and hopefully we can identify some design improvements. So this is a schematic diagram of how a LiDAR operates. Essentially, you have three major components. First of all, you have your transmitter unit, which is usually your laser, and the system that controls your laser. You have a receiver unit, which consists of something that can collect your signals. Some people use lenses, but the most conventional way is to use a telescope, which is connected to a photosensor, and then you have your system control and data acquisition unit. So there are some, I will not bore you with the theory, you can read it in the paper, but essentially we have what we call a LiDAR equation, which is PR here. So as you can see, they have two optical values. This is the backscattering. Beta pi is the backscattering coefficient. Alpha R is the extinction coefficient. And then you need to consider any other contributions to the signal that you will receive. So you have the LiDAR signal, which is PR. You have background noise from sunlight, for example, which is P_D. And you may have detector noise, which is P_D. As you can see, there's an R² in the LiDAR signal. So in order to counteract that extinction at long distances, there's another property that we can use, a quantity we call the range-corrected signal RCS, which is just removing the R², inverse R² behavior of your LiDAR signal. So first of all, we need to establish some kind of model for using your LiDAR in the horizontal direction. So it is a fair approximation to assume that your atmosphere is homogeneous in the horizontal direction. This you can attribute it to different laws, but that is a fair approximation. And therefore, because you have a homogeneous atmosphere, you can assume that your extinction coefficient is constant, which then allows you to relate it to meteorological visibility. And here, the equation V equals minus log of the contrast threshold over alpha is called the Koch-Mitter visibility equation. And here is some example data that I've downloaded from the Malaysian Meteorological Department. And in order to carry out a simulation in the most likely case, you would choose the model V. So in this case, it's 10 kilometers. The next quantity that you need in your LiDAR simulation is beta pi, and that is related to your extinction coefficient via the LiDAR ratio. And the LiDAR ratio is a hard quantity to get, but some researchers have done the hard work of carrying out measurements and calculations for different scenarios. Here, we combine the contributions from Southeast Asian aerosols and also maritime aerosols in order to get a rough value for alpha, for S, sorry, because Penang Island is surrounded by the Malacca Strait. So it is fair to use the Southeast Asian and maritime aerosol values for the LiDAR ratio. So the next quantity that we need to consider is, are there any other contributions to your detected LiDAR signal? The first one would be solar illumination. So the easiest way to model this is to say that in daytime, you'll get something, in nighttime, you won't. And this is the equation that you would use. And some important quantities would be L, which is the solar spectral radiance. You can use information from simulation softwares developed by Moctran, for example, and you would assume that there's uniform illumination of sunlight over the region of interest. That means that along the whole scanning direction, you would assume an equal contribution of sunlight on your signal. And this quantity, solar background illumination, depends on your LiDAR specifications. For example, your filter bandwidth, which is delta lambda, your receiver field of view, which is omega here, and also quantities like A, your receiver area. The last one is your detector noise. So here we treat detector noise as negligible compared to the signal and background contributions. Therefore, we say that PD is 0. This is also the usual case in some studies that researchers have done in the past. So why do we want to conduct a numerical assessment? It is to check if your hypothetical setup is usable under the test conditions that you have set. And for our applications, when should the LiDAR be used? It should be operational in both daytime and nighttime. And the indicators that you need are the signal noise ratio and the range corrected signal profile. So this elaborate expression is the signal noise ratio for LiDARs. And how can we check these performance indicators? First, we have developed the simulations using Python. We conducted a case study using a hypothetical setup. We evaluated the results for maximum detection range of 1 kilometer. And also you need to set a threshold value for your signal noise ratio, which we have set to 1. So this is a numerical assessment scheme that we have developed. It can be generalized for all horizontal scanning LiDAR designs, which means that anyone can use this, follow these steps, and adapt it to your own regional or climate variations. And there are 5 points, 5 criteria that are covered in the comparative study. The first one is your signal noise ratio. Secondly is how noise would affect your range corrected signal. The effective detection range, your range resolution of your LiDAR, and also lastly, eye safety. So here we have conducted a case study. Here are some of the parameters that we have set for the LiDAR. We have set the detection range to be 1 kilometer, which is significantly lower than what LiDARs can achieve. This is because Penang is a densely populated city and has had many high-rise buildings. Therefore, it is out of safety concerns that we have limited the detection range to about 1 kilometer. This is to prevent unnecessary exposure to the laser. So preliminary results are as follows. The signal noise ratio and range corrected signals. From here, we have set the blue region to cover signal noise ratios that are lower than 1. So from the diagram, you can see that we have used 2 lasers, 2 laser wavelengths. 532 nanometers is the usual laser wavelength that are used in LiDARs. 808 is chosen because it's a diode laser with a closer wavelength to the peak sensitivity of silicon photodetectors. And the difference between these 2 profiles is because of the different laser powers that we have used. You can see that in daytime, the green channel, 532, had a maximum detection range of 94 meters, whereas the 808 nanometer channel can achieve 220 meters. In nighttime, they both exceed 1 kilometer. Looking at the range corrected signal, you can see that in daytime, it increases, and that is not ideal, because that means that there is a significant amount of solar noise that would influence your results. Therefore, when you are doing, for example, data analysis in daytime, you need to take measures to remove the amount of solar background noise in your readings. So we conducted a preliminary setup optimization by considering the receiver area and also the full overlap distance for the LiDAR. And basically, we have concluded that you do not need to change any of the settings that we have set before, primarily because of cost and safety reasons, and also because they have already been fully optimized for detection. So now that we have a finalized setup that we can test, we need to select other setups for the comparative study method. And there are a few things that need to be considered during the selection process, which is how similar the components are used in the setups, the LiDAR scanning direction, and also the claimed LiDAR detection range, because it would not be fair to compare an apple to an orange, for example. you would compare between apples. And we expected that the results would mainly depend on the choice of the transmitter, for example, the laser power, or if it's a laser at all, and the optical components. So here we have chosen a Sheena LiDAR, which is a short-range LiDAR that is used in the horizontal scanning direction. And it has a detection range of within 1 kilometer, but it uses an LED. Whereas for this VAST LiDAR, we chose it because it had the same laser channel, but it was used for atmospheric studies in the vertical direction. But we thought that it would be good to at least have a look at how different systems work. So this is how the comparative study is carried out for the Sheena LiDAR. And some points to check are the detection range, for example, the form of the curves that have been generated, and are there any special features to them? And because of those distinctions, we also need to consider why. Is it because of different parts, or is it because of different settings to your system? So some general observations: this Sheena LiDAR, an LED LiDAR, has a low power source, low power LED source, and a short pulse length. Because of this short pulse length, it had a higher resolution, meaning it can produce signals that it can have a range resolution of down to several meters compared to ours. But because of its low power LED, it has a poorer signal noise ratio and detection range. And as you can see, both of the LiDARs were affected by solar illumination. The second comparative study was conducted for this Vietnamese LiDAR, VAST LiDAR, and it uses a different laser source. It uses a high power NIT-YAG laser with a short pulse length. Short pulse length equates to a higher range resolution, but because of its very high powered laser, it has a very good signal noise ratio and detection range. And you can see that it was virtually unaffected by solar illumination. So to evaluate these setups, I have made this radar plot, which includes all 5 points that I've mentioned before. The scale is 0 to 5, with 5 being the best, 0 being the worst. For the Sheena LiDAR, which is the gray one, it has a very high range resolution, and it is eye safe because 394 nanometers is a wavelength that can be easily absorbed by the liquid in your eye, meaning that it won't hurt your retina. However, because of its low power and the short pulse length, it has a poor detection range. Whereas for the VAST LiDAR, because of its very high-powered laser, it can produce high-quality signals that exceed distances of more than 1 kilometer. However, because of this strong laser, it is very hazardous if you do not operate it carefully. Whereas for this hypothetical LiDAR setup, it is more or less balanced compared to the previous 2 examples, and it met the case study requirements. However, the range resolution is poor. You can only sample the LiDAR at intervals of about 50 meters, which is not great. And the daytime detection range can be improved. So how can you do that? In order to improve your range resolution, you can use a shorter pulse width. That depends on the modulating system that you're using. And in order to improve the signal noise ratio, you can use a stronger laser, for example. But because a strong laser has a high energy that is incident on your eye, you also need to consider using a beam expander to improve the maximum permitted exposure. So to conclude, I know it's been a very wordy simulation paper, but to conclude, we have presented a numerical assessment to evaluate the performance of horizontal scanning LiDARs using a comparative study method. This is important because we do not need to physically assemble this unit, and we can use a case study setup, which is hypothetical in nature. We use Python to develop the simulation algorithm and software. Basically, the important theory required are the LiDAR equation itself, and also how we model the horizontal atmosphere using the Koch-Mitter visibility equation. To make this adaptable to different settings, we use daytime visibility data that is downloaded from the Malaysian Meteorological Department, and also solar spectral radiance data from MODTREN. I've mentioned the signal noise ratio and range corrected signal results, and the comparative study results. Overall, this hypothetical setup has met case study requirements, but it is not the best. And this method, most importantly, has achieved, without experimental data verification, some potential design flaws that you need to address in the laser module before you proceed in your development process. And also it allowed us to evaluate this setup performance. And because this is a purely hypothetical setup, the case study has demonstrated that you can use this to test horizontal LiDARs in general, so anything at all. So how can we use this, this new method? It can, first of all, help optimize your LiDAR design and development process. And it can also be used to complement theoretical models that involve LiDARs. So this article, a multiple scattering theory approach numerical model for haze detection using horizontal scanning LiDAR, is my second work, which is currently on revised submission, which is under review. And we use this comparative study method to design a hypothetical LiDAR, which is then used to verify multiple scattering theory. And we hope that this method will also be able to contribute to the sustainable development goals. So if anyone is interested, you can get a copy from me, or you can log on to Optics and Lasers in Engineering. Thank you.
Questions? Yes.
Are you planning to use coherent heterodyne detection to improve the signal to noise ratio, or will you LiDAR?
So generally, because we are just dealing with signals, the simplest cost-effective way that we usually try to use is to just ramp up your laser power to be significantly higher than your background. But because in the end, we are just using, for example, oscilloscope readings and applying inversion algorithms to them to get important properties like extinction coefficients or backscattering coefficients. Therefore, that in itself is already not very accurate. So, and it is not completely indicative of aerosols generally. So I think, I'm not sure if that would be a great way to improve signal noise ratio, but just from my experience doing my PhD and reading, the general way that people use is optimize hardware first before we try to optimize software, but thanks.
I have a hard comment, hard question. So your model is quite general, but focused on application in aerosol detection. More generally, you can use LiDAR, for example, for three-dimensional imaging,
yes,
autonomous vehicles. So, but if you go to more general models, the selection of the wavelength is very important. So you already mentioned some points, but I'm talking about really looking at wavelengths in the telecom wavelength, like 1.3, 1.5 meters. And there you have all kinds of issues, like what kind of cost-effective sources you have.
Yes.
Diode lasers, higher power detectors. Okay. Then you have eye safety issues. And if you go to 1.3, 1.5, it's much dramatically better than 0.8.
Yeah.
And then you have even the solar radiation issue appears because you have some dark lines in the solar spectrum at certain wavelengths, which we move back up. So how is this figuring in your broader minded consideration?
So I think generally for LiDARs, because you need something that is a laser in itself that is high powered, and for elastic backscatter LiDARs, you use pulse systems. So generally in the literature and also from scientific research, people have found that a wavelength of 1064, which is the base wavelength of NIT-YAG lasers, they have significantly lower effects. They encounter less effects from water vapor, which is a huge problem in our atmosphere, especially if you want to consider solely contributions from aerosols. So because I'm working on aerosols, yeah. But that in itself is a problem because detectors aren't great in the infrared unless you purposely dope them. Going down the wavelength spectrum, 532 is the second harmonic of the NIT-YAG laser, and that wavelength is close to photomultiplier tubes. So I guess it's just a matter of like striking the balance between the limitations in what wavelengths you can achieve using lasers that you can buy. But I understand that, for example, when LiDARs were still used in autonomous vehicles, they chose a wavelength of about 900, of course, with the specific detector, because 905 nanometer has a very low spectral contribution from sunlight. So if you take the necessary precautions by selecting your optical components very carefully, then you can basically ignore any noise from the background when you're using some wavelengths. But yeah. Thank you.
I think that's an excellent constraint.
It sounds like a viva for my PhD.
Yeah. Thank you.
Thank you very much for your information. This is the end of the morning sessions. Now it's time for lunch. You have the ticket for lunch in the back of your presentation. It's here in the restaurant. Okay, and after lunch, they want to take another picture. Okay, so just remember to take another picture after that. Okay.
I don't know. I don't know. Maybe you are happier because you have just eaten. So
Let's make a photo. Because I also have need a photo. Thank you.
Thank you. Okay, so we'll see you then.
No,
לא, וגם פחות האנשים מחכים לי. וגם אני מנסה להבין את מה אני עושה עם... כן. נכון, אז תשמע, יש לי מלא...
Still missing my son.
Yes, one of my former postdocs, he went.
So I just use someone to give us.
No, it's not the scholars conference is there.
Thank you. Tomorrow is all day virtual, I think. Someone is. Do you?
Yeah, that. Oh. This is good. Oh, no. Oh.
What's in? Yeah.
Better you use is quoted, right? The better you use is quoted. So what's in the next one?
The method was not quoted. It was pure barren steel, and we applied the graphene, but there was no DLC on the. Yeah, what to say, if you remove all the rated fabricant on, then we spend it to the DMF graphene. Yeah, that's not so much illuminates.
Okay, what do you use today?
The photonic part, we have also some ultrasonic horn with much more power. This was the first steps. Then it was dipped inside. Try to
Drop inside.
Yeah.
How you control the flow of what? The liquid.
Right, that can be all optimized. Yeah, of course.
Now, if you are just dropping it into solution, that means there's simplicity that we have put it inside as well.
Yeah, and put it everything. So you have something like this agglomerates, but you can see here it's also a little bit dark, right?
Yeah, you can see.
Yeah. Yes, but also some dark.
That's what I'm saying, that you cannot control. There's a way to control distribution of this. Because that's where the switching and distance.
Yeah, I think some spray coating would be better. I use spray, and when it's heated before, then
it's just an idea. If it's sprayed, you're going to control the flow of spreading. And by doing that, you have a uniform and consistent loading of the graphene from the wall of the BNM case. Very easy case to
our friends from the Project Institute, they want to use a press. We have a running, and they take a press and push it. Then we also define layer. They put the solder, then take a press, form, put it spread it, and then it's also a very thin press layer, but of course, then we'll get something like with the graphite graphene layer that have to be researched also.
Yeah.
Have you had this in blood condensers?
Let's get it right. You have to chase it down. No problem. So that this is mine. Just pass on copy. Very well. This is. If you let me one. I'll just one. This is mine. Not mine. What's very similar? Not mine. The smaller one. The out of that is true. Then this. Yes. Yeah, yeah. Make life easy. Yeah. Much easier for you. You're not going to be children. You are.
Me.
You want. Are you still staying?
Yeah.
Yep. Yes. It should take a few chance. So if it's a direct, are we starting? It's about 30. Yeah.
It's freezing in this room.
Yeah.
Right? Everyone agrees. So let's go and think about it. Yeah. It's there.
Yeah, this is the time.
Yeah. So
Oh, wow.
Yeah, yeah.
Ah.
9:20. Right, about
22. Let's see. 22. I'll let you know.
Yeah, 9.
זה 19 בתוך החדר, במצב סטטי, בשיעור פילאטיס זה נהדר. אפילו חם מדי. רגע, אז מה אני אעשה כדי שאני לא אפשל בהרצאה? אם אני אפשל, אז זה לא נורא. רק אתה תדע.
There's a story. Yeah.
ועוד אחד שיושב שם במרכז הנעמי. במרכז ננו. עכשיו אני קודם כל רוצה לכתוב את זה. רגע, אני לא הראיתי לך אותה מזמן. בטוקופאיה ישבנו פעם אחרונה ביחד. בנס ציונה. קודם כל זה היה פורים וזה עוד שאני מגיעה לאופן. כן. וזה את קנית לי מכונת קפה חדשה שתפה.
דרך אגב, זה מאוד פשוט. זה חלק חשוב מאוד.
ברור. זה ראית?
Yeah.
Okay.
But tomorrow there is to me. No.
מכל הסמינרים מקרים.
Yes. Currently, I'm working with the okay. So after, so you can find the best example. When do you want to do that? My mind is my dad. You do just want to. Oh.
כן, בכל המדינות, הם כנראה גם נוסעים לתל אביב, ויש...
Oh, sorry, about that.
רגע, אני חייבת ללכת לשירותים.
Yeah. Yeah.
If you can knock it for it, you can stand. You can stand.
Yeah.
And that is a
Because I think that.
Yeah, yeah, okay.
Yes. Yeah.
Very good. Yeah. Might be. Thank you. Okay, let's see.
Yes.
Yeah, Mr. Joseph can please start next presentation. Yeah, okay.
Yeah. Are you online?
Yeah.
Where is the folder?
Welcome back. Welcome back from lunch, everyone. I know that after lunch, conference number used to reduce in the room. But notwithstanding, I'm here to. Excuse me.
Yeah, fine.
Transition mode. That's it.
Wait, this one, right?
Yeah. Yes, I'm here to present to us the thermomechanical characterization of bioplastic film produced from combination of polylactic acid and bio-nano-calcium carbonate. When you enter into this place, you see a banner by the side. They were telling you that please help us to reduce carbon content. That they wanted to help them to reduce carbon footage, carbon footprint. We discovered that plastic have been our everyday life. If you ask me, the cover of your phone, most of them are made from a plastic. Your pen, they are plastic, right?
No.
Your clothes, most of the clothes now, they are made from plastic, polyester. Our television at home, your laptop covers, they are plastics. So now, and all these plastics are made from oil-based material or chemical-based material, which make them to cause havoc around the world. They have been linked to climate change. They've been linked to different kind of mosquito breeding that turn to bite men and turn to malaria. Many health issues, and we should look for a way of reducing this. Why is people using plastic materials? Because they are of low cost, they are durable, and they are lightweight, and that's why people are demanding for it in such a way that so that they can produce a lightweight material. An increase in plastic demand is because of different application. It's now being used for drug delivery. It's used for packaging, different packaging, both in food industries. Food industry, they're making of it. Many industries, they are making use of it as a plastic, as a packaging. Now, the increase of these materials, the increase in demand for these materials, increase the waste that's generated from this material. And these wastes are now deposited in our environment, generating excessive heat to the atmosphere, turn to cloud that fall down as rain and destroy lives and property. The alarming impact of plastic litter is now a serious concern. I think in Mississippi yesterday, the tornado or something, the express tornado that wipe away houses. So we have to remove this plastic from our environment to have a better and safer place. You can see the nuisance. The nuisance caused by the plastic in the environment is still leaching. You can see this effect on the land, and you can see this well. This well was washed with the soil because he swallowed plastic, we call them microplastics at the sea. Now, why do I have to develop this bioplastic? People are going down to the source. If I bring up, people are going back to the roots. If you ask me, everyone we want to go back to tree, plant, bioproducts because they have lesser effect on environment and life. So why do you want to go there? Common plastic such as starch-based polylactic, PLA, and polyarthropodene, PHP, and non-toxic, and they have no health concern. If you introduce such material into our environment, we have lesser problem in terms of health issues and climate change. Secondly, many bioplastics are naturally occurring and they don't have carbon footprint. So we can help this hotel to reduce their carbon footprint by producing these materials. And most of the material that we have here, like polyester, polythene bag from what do you call it? From shopping malls, they are made from polythene and they are oil-based materials. They have minimum impact on environment because they are degradable, they are recyclable. You can take them, recycle it, and get whatever you want to get from there. They have, however, these materials, they have poor thermal property. If they are subjected to thermal stress, they degrade. The molecules will start dissolving, and it will reduce the bonding between them, and they will fail. We'll be able to see any of them. So we should look for a way of increasing this plastic. However, the oil-based plastic that we have here, that we have available now, they have this better thermal property compared to bioplastics. And the loading effect of these nanoparticles on thermal property. Now, to have a better material, plastic material with improved thermal property, we have to add something to it to increase their thermal property. And that's why we consider something. We consider snail shell. Snail shell is a waste. We're just trying to get a waste and a waste together to get something. It's a waste that is in South Africa, they rear snail shell, and 445 million tons is still needed in France. France consumes snail. And according to literature, more than 150 million kilograms of shell are produced every year. So if they are produced every year, this is just the snail, the flesh. What are we going to do about the shell? The shell they are using as a landfill. They throw into landfill, and now we don't have enough space because we have a lot of waste to take care of. Also, why are we making use of it? It has high concentration of calcium carbonate. I synthesized this material because it was my PhD product program, my result, one of the inputs. I synthesized it and I got 100% calcium carbonate from this snail shell. We have 2,500 species of snail shells, but these shells I'm talking about, it has 100% after decantation and stuff, all the method that I used to get my calcium carbonate. Also, he has better thermal property. He has stability up to 840 degrees C, which if we dope it into a plastic material, there's tendency of it increasing the thermal property of the bioplastic. They are available at no cost. They throw them into the bin. They throw them, you see them on the streets. Nigerian, Cote d'Ivoire, they are the highest, after China, after France, they are the higher consumer of this snail, but they just throw this thing on the floor, throw it on the streets. We go to our drainage, block the drainage, go to the sea, cause havoc that we are facing up to now. So that's why we make use of this. Now, considering this bioplastic and the application, where are they used? You can see all these materials are used to produce bioplastics. But if you consider this one cellulose-based bioplastics, this one, what is still going on it? This one, they are oil-based. This one, you can get this from what they call cornstarch, but they still have starch, this and this. They still have competitive, they are competing with food supply, which we are looking for a way of reducing its weight. Cellulose. This cellulose is a place that people are seeing, they are just coming up, but most research are focusing on different PLA and PHB, like I mentioned before, to produce a new materials. If you can see, why do you want to do it? Because we discovered that the market segment is increasing. You can see, look at all these places, this where is applicable. So if we produce more, we reduce the amount of waste produced from these companies, which will reduce our problem in the world. Now, we know why we want to do it. We know where it's going to be applicable. We know the problem we want to solve. So how do we produce it? We put it, you can see, we suspend, they come in micro, it's like flat pellets. They come in granules, small particles. So we have to dissolve them. We dissolve them with a solvent. It was there for like 72 hours. Actually, we have developed a new method of dissolving it within 1 hour using another solvent. So we get it to this point, we stir it, we put our nanoparticles, the snail shells, inside it, we stir it together. We pour it into a glass where it cured. We got something like this, dispersion, and you can see the linkage. These are in the PLA and your nanoparticles here, and at the end of the day, we get this. The polarity of loading was between 195, it's 100% rather, and the loading of calcium carbonate that was produced from Argentina folica shells were from 0 to 5, and we make use of solvent casting to produce the plastic. After that, we have to investigate to know if truly we have improved plastic with improved thermal property. We make use of we use FTIR, fluorescent transformer infrared spectrum, to see if the chemical the solvent used to dissolve that material, we have effect on the property of the plastics itself. So we discovered that thermal property, we check the thermal stability and material degradation of this material. And DNA, we used to measure temperature dependence, storage modulus, loss modulus, and plant data. So you can see this is the weight. Here you can see that it should these are polylactic acid, PLA, and these are the materials that they're loaded, the PLA with loading of nanoparticles, which is calcium carbonate. You can see the difference that it increases the thermal stability, right? And that's what we want to achieve. Additional significantly increase the thermal, it increases the temperature region from where it was here to that place. This was around 198 degrees to 360 degrees centigrade. And also, we discovered that bioplastic with lower concentration of 1% has the highest, it exhibits almost 51% of increase in thermal property. And the thermal performance can be attributed to inherent property of the nanoparticle that was loaded into PLA. The same thing
This is a study modulus, temperature-based temperature modulus. We discovered that PLAs have a decrease. This PLA here has a decrease, and as we load it, we dope it with nanoparticles. We have increase in at this region, which is at 20 degrees centigrade, and we discovered that in incorporation of that and loading up to 3%, up to 3% give us the highest story modulus. Also, we discovered that addition of this performance based on the ability of forming good interconnectivity of both PLA and nano calcium carbonate, which at the end of the day give us a formidable structure that have better resistance to thermal stress. The same thing happened to loss modulus. We can see that up to 3 showing the best result. But we can see that there's insignificant between 3 at this point here, between 3 and 1. And economically, we can see at 1% doping, we can have better results. And the stiffness as well. The stiffness is resistance to external thermal stress under variable loading rates, and temperature provide is physical elastic time dependent property. And we can see that as this PLA, as we continue loading, it increases. And plastic with non-particle exhibited a significant margin of 84 points, higher than that of PLA. And this can always be attributed to the inherent property of calcium carbonate, which has a. Now, I make mention of FTIR. FTIR, we just use it to check if there will be any changes in compatibility of these materials. If the solvent that is used to dissolve that material will have effects on it. And we see that there's no significant effect, because all these peaks, the peaks here are PLA. This one is from the calcium carbonate that was used for it. Okay, this one was from this one from solvent. From here to this place is PLA, and from here, somewhere here, from 700, 800 is the calcium carbonate. And based on the facts, we discovered that we were able to develop a biocomposite that will improve thermal stability, and all the thermal property that investigated was improved irrespective of loading. However, if you consider the economic of the material that was put together to develop this, we discovered that film with 1% will exhibit a better property and can be. Now, this material can be a material suggested. It can be a material suggested for maybe food delivery, because it have no effect to food. Thank you. Any question? Okay.
Which method you opted for this manufacturing method?
Yeah, I use ball milling method.
What you go with the other methods also? Is
Is
there any specific reason to select that ball milling method?
Yes. Actually, there's another paper I've just written that I make use of a supermass collider. But if you want to ensure the, how can I say it, the toxicity, the pureness of this material, I would suggest that you go with boil milling. And even if you are doing dry milling, there's tendency when it's above, when it's lesser than 50 microns. I mean, your material, you see, it will agglomerate and it will become like a block that won't be able to separate again. So even from that boil milling, we use 2 processes or 3 processes
I have my article is there. You can see the operation of this material, the million of this. So you can use any other method. I cannot say that it's going to work for you unless you test it. That's why it's research. Check research, you get another result.
And can you use, are you using FTIR for identifying bioplastics and plastics which are derived from oil?
No.
Because imagine if you want to have zero plastic, then the government is thinking that they can use FTIR to identify bioplastic and
you can use FTIR to identify both oil produced plastic and bioplastic. Why? Because we have FTIR spectrum.
Yeah,
and with those figures, you'll be able to know which group they belong to. This material belongs to carboxyl group.
You have this carbonyl group.
Carbonized group. This is carbonized group. So which is 0% is about plastics. So
there are some synthetic plastics which one is plastic which have that zero bond also.
you said?
There are some synthetic plastic which have that also the zero bonds which are not bioplastic.
Yes, those plastic they are only recyclable. They are recyclable, but they are not biodegradable. Yeah.
So you can just use FTIR.
You can use FTIR to differentiate because it will show the group they belong to.
Yes.
So with that group, we're able to identify which class, under which class they belong to. But in this process, we know that the materials, because from the, it's just one part of the way. From the beginning, we have tried not only FTIR, we make use of EDX to identify the elemental component. So when we get the elemental component, we bring it back to FTIR. If you check previous paper before this one, if you check FTIR, we discovered we have known all the, so now we know that, but we just want to see if the solvent used to dissolve PLA, we have effect on the carbon group, so we know where to classify it. Maybe we have to classify it under synthetic, or we have to classify it under biodegradable. Have I answered your question? Thank you. Any other question? I'm the one moderating, I'm the one presenting. That's very good. Let's have it.
Oh.
That was me. Okay. I think I have to help from here.
Yeah.
So I want to welcome Ms. Dana as Laman from Kenya, Abdullahi University, Science and Technology. It's not yet. Not yet. The last person will be Siriwan.
Yes.
From the Neri University of Technology, China. Yeah. Yes. Conductive material from automotive industrial waste. She was born in Nakhon Ratchasima, Thailand in 1987. She received the BTech and MTech and PhD degrees in ceramic engineering and from the Neri University of Technology, China in 2008.
Thank you for special chairman.
Dr. But yes, you don't get a certificate, right?
Maybe this isn't me. Can I? How can I do this? Then?
Yeah. Yusuf, please. I first point.
Okay.
It's not coming. It's on phone. Who's presenting? I don't know who's presenting. Prof, this one present the certificate to you. Thanks, Prof. Yeah. Shake hands. Shake hands to me. Oh, it's gone.
Is this okay?
Yeah. Yeah, you can carry.
Okay. Okay. Thank you, my special shaman. Thank you for introducing me. Naka is mean. Naka is the language in Thailand. Okay. Okay. Let's start to presentations about our work. Actually, I have apologized to you all because of I'm not perfect in English language and also don't understand in English so much. Okay, but this is your problem. That's my problem. Okay, try to understand what I want to say. Okay. Okay. Today I would like to talking in the topics of conductive material from automotive industrial waste. This is my work that now I am focusing. So my name is Sivan Chokha from Suranari University of Technology. I'm a teacher in Suranari University of Technology. In the rest, I have divided my presentation into the 5 parts. The first of all, sure, I would like to introduce you about how to get the automotive industrial waste and how to use and how to decide about the waste management. And after that, I will talk to you about how to use the FE waste of the treatment as a dopant material for synthesis of the conductive material and use it in the cathode ITSOFC intermediate temperature solid oxide reaction. So the next part is the objective and exploratory side, results and discussion, and also conclusion. I don't know about my slide. Earlier like that. Maybe earlier same like me, you know, because of now it is nearly time to sleeping in Thailand.
No, yeah.
And I arrived in the middle nice. And this is my first day in London. Okay. The automotive industrial waste is increasing rapidly to meet the demand of using the car, you know. And in Thailand, the automotive industry produce many of waste, and it's increasing years by year, and around and the automotive industrial waste per company show the waste around 100 tons per year per a small company. And in our country, the removal technique that we use is paying the money. It is so high money because of we will paying the money around 1,800 baht per ton. And the removal technique that we also use in Thailand is the landfill. So that is the effect to the environmental, you know, because of if you use the landfill technique, the waste also have a lot of the iron, so it can react with the oxygen or something like the nature method. it is effect to the environmental and also effect to you all. After that, to solve this problem, our team focusing just about sustainable waste management, that we focus on how to use waste and increasing the values of waste. That means after we got the waste from the industrial waste, we first of steps, we also decide about the waste management first, and after that use the waste from treatment, after treatment into the use the waste from the after treatment and use some kinds of the acid react with them, react with together, and after that we will got the chemical compound, a new chemical compound, and a new chemical compound that we found that is show the high impurity, same like a chemical gas. And after that, the final step, we use the chemical compound gas as the starting material for the new structure, like a conductive materials that we study. Okay, the conductive material that we focusing, it's just solely the cathode material and used in the ITSOFC, intermediate temperature solid oxide fuel cell. The intermediate temperature solid oxide fuel cell, this is a device that can operate the electrical conductivity by electrochemical in the new unit cell, and the unit cell of ITSOFC consisting just three main components like a anode, electrolyte, and cathode. But in the inverse, we focus just solely the conductive material such as cathode material. And the cathode material used in SOFC have a lot of the structure, a lot of structure like a perovskite structure, double perovskite structure, and also Ludersen-Popper structure. But however, there are many researchers about the other structure, but it concludes that the perovskite type show the highest of electrical conductivity more than other structure. But however, even if it shows the highest of electrical conductivity, but it also shows the disadvantage also. The disadvantage that we found that is the high thermal expansion coefficient. The high thermal expansion coefficient is the effect. It can affect to the crack in the unit cell after you use some with other material, and the material, for example, the cathode show the highest of thermal conductivity, right? And the electrolyte show the lower of thermal conductivity. It is the difference of the thermal coefficient of thermal expansion, so that's why it will crack. It will get the crack and get the cracks in the unit cell, so it's affect to the long term of the device. It is a short time for using. So, however, and another one is the degradables of them. So many researchers have to solve this problem by using the transition element. That is the reason why we this we focusing on the waste because of we found that the waste from the industrial waste have a lot of leads of iron oxide, iron metal, you know, iron metal, and the iron metal is the sum of transition elements, right? So that is our work that I need to focus. So in this work we use Fe iron oxide as a dopant material for synthesis of the lanthanum nickel oxide. This is a perovskite structure, and after that we focus just solely the x equals 0 and x equals 0.4. X equals 0 is the base material, does not have the iron oxide, but x equals 0.4 it have the iron oxide, maybe it have the weights inside, right? That is our objective. And this work is the preliminary of study on use of automotive industrial waste as the precursor in the synthesis of conductive material. That is beginning. Okay. For our experimental design, there are 3 steps of our work. First step, after I got the automotive industrial waste from the industry, I washing with the water, and after that remove some impurity like a grinding wheel powder by using the magnetics, and then dry and sieve again and check the property first by using the XRD, X-ray diffraction. And after checks the property, the basics of property, I use the nitric acid to react and form to be the new phase or the single phase of iron oxide first. Before using the iron oxide form waste, I also check the structural first, and then using it as the dopant materials for synthesizes the lanthanum nickel perovskite type with X equals 0 and 0.4. And the technique that we use for synthesis is the traditional technique. Actually, we you know, it have a lot of the technique that used for synthesizes a new material, but this is the preliminary, so that's why I use just only the basic technique like a solid state reaction. Maybe you can know about the grinding mechanical, grinding mechanical or something like that. Okay, and then after that the powder will dry and steep again, and also calcination at the temperature. The temperature that we use is around 1200 degrees C. And then the property will check again about the structural phase. And after that, fabrication in the bar shape, and check the and before checking the basics of the properties, I also check. I also bring it to sintering first. Okay, and using the same temperature, same like a calcination temperature. The property base that we focus is the solidity, like a structural characterization by XRD. And also, this is a conductive material, synthesis of conductive materials. So the property that we must check is the electrical conductivity also. The electrical conductivity that we use, the technique that we use is for probe DC method. That is for cathode material. And then finally, thermal expansion coefficient by dilatometer. Okay, this is the result and discussion. The first step about the waste management, right? The table 1 show the chemical compositions of iron waste by XRF, and it found that it's not too much significance of the amount of iron. So it means like the waste that we got is show the higher of purity of Fe iron. So in this case, the waste that we get from the industry show the highest of the iron metal is higher more than 97%. It is nearly or similar to the chemical gas of material of chemical gas of the chemical compound, chemical powders. So after that, we use the XRD pattern for check structural phase inside. And it shows that the mixed phase of Fe metal with iron oxide. The iron oxide show the iron oxide phase that show in the waste is occur because of Fe react with oxygen and react with moisture in the process. So that will show the mixed phase of them. Okay. And the next one is the X-ray diffraction also. But the X-ray diffraction of the X-ray diffractions of this slide shows about the properties of the step 2. You know, after we found that the waste material show the highest of the iron oxide. So and after heat treatment and after treatment, we use it which react with the nitric acid, and after that we got the new phase of them. So the new phase that occur after react with the chemical, it show the single phase of iron oxide. It's resulting to Fe iron disappear. Fe iron react with nitric acid and form to be iron oxide. So that's why the iron oxide is increasing. And it shows the single phase around 100% of iron oxide. For the next result is after we got the iron oxide from the waste and show the single phase of them, we use it as the dopant material in the perovskite structure. This is the first of all, this is a base material without iron oxide. We use the calcination temperature from 800 degrees C to 1200 degrees C to study about the optimum condition for calcinations of this structure. But if we focus in the lower temperature, the lower temperature does not compete about the react between the starting material and form to be the phase that we want, right? Because of it still have the starting material inside. And however, if we increasing the temperature and around 1000 to 1200 degrees C, the lanthanum nickel perovskite type increasing, and by the way, the starting material decreasing. But in this condition, it still have mixed weight of the lanthanum nickel perovskite type, which some remains of the starting material. And the next one is also, but different from the last one, because of the next one is we use iron form waste as a dopant with X equals 0.4 inside. And the results also same. Like when we use the calcination at lower temperature, the starting material also remain in this powder. But after we increasing the temperature of calcination, the new phase of the perovskite increasing, and by the way, the starting material also decreasing also. In this result also almost same. Even if we use the highest of the temperature, it's more than around 1200 degrees C, it still have the mixed weight of the three phases like that. You can see in the table 2. The table 2 is the conclusion of the powder that we try to calcine at the 1200 degrees C. For the base material, without iron waste oxide, it shows the mixed weight of lanthanum nickel perovskite type, which higher amount around 99%. But however, it still have the starting material inside. And the other ones is iron form waste as a dopant that we use. It also shows the mixed weight. The mixed weight that we found out is the weight that we need, right? It shows the highest more than other phase, but around 53%. But other phase that we don't need, it still have. So this is a percent. This is percent analysis by Topaz analysis. Okay. After that, we bring it for fabrications in the like a bar, and testing about the electrical conductivity by using the 4-pole DC method, and showing the figure 5. The figure 5, the electrical conductivity that we measure with the temperature. Why we use the temperature for measuring the electrical conductivity? Because of the SOFC can produce the electrical by using the temperature inside, right? So the temperature that's being used is the operating temperature for the SOFC. So that's why we focus the room temperature to 800 degrees C. This is the operating temperature for ITSOFC. The picture left hand side, right? Left hand side. The picture left hand side is the lanthanum nickel base without Fe iron, and the another one is the lanthanum nickel iron oxide perovskite type. The left hand side, the electrical conductivity that we found that show the matrix behavior. It seems like the electrical conductivity decreasing, which increasing the temperature. By the way, after we dove with iron metals, the electrical conductivity change from matrix behavior through the mix of electrical conductivity, with the semiconducting behavior and matrix behavior. And for this material, from room temperature to around 550 degrees C, the electrical conductivity increase with increasing the temperature. It seems like a semiconducting behavior. And the optimum of 550 degrees C show the highest of the temperature of specimen, around 40 to Siemens per centimeter. Even it's lower than the base material. And however, after we increasing the temperature from the optimum temperature to 800 degrees C, the electrical behavior seems like a matrix behavior. The temperature increased with the electrical conductivity decreased with increasing the temperature. Okay. And the finality of our work is the experimental, it is a thermal expansion coefficient. This graph shows the thermal expansion coefficient by using the dilatometer. We found that after we dove it with wedge, if iron wedge inside, the thermal expansion coefficient decreasing from 13 to 12. It is similar to the electrolyte that we use for ITSOFC. Huh? This is come up? Whoa, sorry. Okay. Final slide. Okay, the conclusion that we found that the first of all, we can make the single phase of iron oxide by using the nitric acid to react in the new chemical compounds. And after that, the structural that the powder that synthesis by using the iron from waste after calcined at 1200 degrees C is the mixed phase. And the base material does not have the iron waste, show the highest conductivity more than dopage with iron waste. And then finally, thermal conductivity, thermal expansion coefficient that we found that after we use iron oxide as a dopant, the thermal expansion coefficient is lower than the base material and is similar to the electrolyte material that's used in ITSOFC. Wait, listening? Thank you.
Let me speak to her.
Well, so you show transition from semiconductor to metal behavior around 500 degrees Celsius, something like this. That's about 800 degrees Kelvin. So the semiconductor has a band gap of about 60 MeV, I think.
Yeah, I don't.
If I calculate on this. The transition from semiconductor to metallic, I think it's because you excite carriers from the valence band to the conduction band.
I'm not sure.
Semiconducting behavior. There's a band gap.
Yeah.
In the metal, there's no band gap.
Yeah. It's overlap together.
So the band gap is like the thermal energy at 500 C. Yeah, thermal energy. Okay. So my question was, can you control this transition temperature by changing the composition of the peroxide? If you change, you start from this peroxide, what is it, lanthanum, nickel. If you choose another one, this temperature will change also. This is my question.
That if you change another, if you take another material, aside from learning this learning 0.6, maybe the behavior of the material will shift on this side.
Okay. If we change the other material, the property also, the electrical property also change.
Change.
Thank you very much.
All right.
No.
Yes. As that is done, I'll be calling
Thank you.
The big man Natalie.
So I can give a certificate.
Yes.
Certificate of appreciation. Very good.
For Rebecca. She's from the University of Langen,
Thank you.
Germany. Rebecca Natalie is a scientific assistant at the University at the Institute of Polymer Technology, Randrick, Lysander University, Erlangen, and then our current program is a GFG, German Research Foundation project on the production of achromatic lenses using composite injection molding of transparent carbon materials.
I think it's going to no.
Share with. Yes.
Yeah. I'll try to put this over here.
Yeah.
Perfect. Yeah, perfect. Let me check if this works. Perfect. Okay. Thank you very much. Okay, welcome. Hello, everyone. I'm going to talk today about improving the optical properties of achromatic lenses with the process parameters in injection molding. My agenda for today is going to be introduction and motivation about the topic. State of the art, how are optical lenses made out of polymer now? Scientific goal. Then afterwards, I will talk about the experimental procedures. How did I characterize my lenses? And then about the results. So as we all know, glass is it's more used when we talk about lenses. But if we see the advantage of polymers, we can say that it's the weight is lower, and it's also easier to manufacture and also cheaper. But the problem is we have some negative part in the polymers, and it is that our optical properties are not as good as in glass. So we have, for example, transmission and dispersion are two of the optical properties that are not that good. So this is why I would like to, or this is why I'm doing now my research on achromatic lenses. Achromatic lenses should help with the dispersion of the material. If we have, for example, a biconvex lens, we have the light, and then we see the achromatic aberration of the light. But if we unite biconvex lens with concave lenses, we can reduct this, make a reduction of the chromatic aberration. So that's my motivation for today. We are going to talk today about the optical properties of the achromatic lenses. At the first part of it, I'm just kind of starting with the project. And but it's important to know that in achromatic lenses, it's not only, but in polymers, it's not only the optical properties what is important. It's also very important to know the bond strength between both polymers. We are talking about two different components, and also the geometry because of the same. We are talking about two components, and when they are unified, we have to see that it's a clean surface between them both. I would just start quick with some background on optics. As we know, we have when light comes from a medium 1 to a second medium, it breaks, and that's what we call the refractive index. But what for me is interesting is the dispersion. Dispersion is lights come inside, and then it breaks each wavelength in a different angle, and this is what chromatic aberration causes. When we talk about polymers, we can see here, this is the area where glass is now, and polymers, for example, polycarbonate or PMMA, in other words, plexiglass, it's here and here. Other number is how you characterize the dispersion of the polymer. We can see it here. Dispersion is right. But it's a constant from the wavelength. I mean, you have the wavelength, it's like explained here, and then you have like in which how is the angle in it within the break. So you can see here we have a refractive index with the dispersion. This is let's call it summarized, and here we have it with the wavelength. If it's bigger, then the refractive index is normally going down. As you can see here, you can find the PMMA, this one, and PC, we can find it here. Important is for the achromatic lenses is that we use two polymers with a different dispersion. They have to be, for in this case, it's going to be polycarbonate with 32 and PMMI with 58. So how are lenses made now? This is the state of the art. How are polymer lenses made now? We have, for example, compression in this solidification. This is in compression injection molding, not the normal injection molding. That means we have the mold is not completely closed. We inject it, and then you can wait a certain amount of time before you close it, and then you will have extra pressure. What my colleagues did with the compression induced solidification is you can say, okay, we can compress it in a isobaric way or in a isopore way. The meaning of this is that you can the molecules inside of the polymer, they are going to, let's call it, freeze because of the pressure before the time it should be. And by that you can control really good the geometry of the lens, that you don't have any curve when it should be plain. And other thing that state of the art that it's also kind of what we're doing is multi-layer injection molding. In this case, these three persons did the research on how to make the lenses also geometrically better, because if you guys think, we have when you injected a mold, a volume in the injection molding, if you do double of this volume, you will have 4 times of cooling time. So lenses are normally a really thick component. So that's the reason why they were looking on ways on how we can make lenses and reduce this cycle time. For example, from Rubik, we have here, they made 5 different ways on how they can make the lenses. Each one better than the other one. If you see here, it's potential of the cycle reduction, and each one is like the component is a with insert process. This is for me important, but the thing is, they both research only look for the same component. Like, first component is the same as the second component, but in my case, I have to do first component, and the second component is another polymer. So I have to do the research almost separately to do it then together. And that's how we come to my scientific goal. It's a study to how to improve the optical properties using my process parameters. Here I will talk today about normal injection molding. I'm not in compression injection molding yet. This is the first part of the research. And we have parameters like mold temperature, melt temperature, holding pressure that I have RI. And important is here we are going to talk about variotherm and isothermic injection molding. My materials, as I said, is polycarbonate and MMA. It's also called polymethyl methacrylate, and plexiglass for normal. So as I said, we are going. I did it with standard injection molding. The machine is an Arbor 520S, and it's an insert process because I did first my polycarbonate part, and then the second one was my PMMA part. And for these are going to be isothermic and barythermic. So achromats are normally the shape that I showed before. It's biconvex with a flat concave. But for the research, I have like a dummy part, which is a disc. This is better for me. For example, I will show today the influence with the contact area between both of the components. And for me, it's here easier to see what are these, what does the process parameters do to my component at the end. For the experimental procedure, I will have 3 parts, so 2 parts. The first part is going to be the polarization microscope. We are going to see the residual stresses inside my polycarbonate part. Then these parts were annealed. That means they were in an oven over a time. And then I have a microscopic analysis of the contact surface after I injected the second, I overmold the second component. So for my first component, the polycarbonate, I had these process parameters, which I vary. The ones in bold are my reference parameters. And here I have a small diagram to just say what is baryothermic injection molding. This is, as you can see, this is the mold temperature on the y-axis and time. So what we do is we take the experimental temperature, in this case, I don't know, 120 degrees, for example, and I just heat the mold until, in my case, was until 250 degrees. And this time, I just wait. It's not a time where I injected or anything. Then, when this time is reached, I can do the injection, and I can do the holding pressure. In this case, that is normal injection mold. And then afterwards, I cool down my mold with the cooling time of the part. Okay, and that's what baryothermal injection molding is. So for the second component, the same. Bold means reference. You're going to see it afterwards. And yeah, so that's I have varied each of these parameters. And then you have here insert process. Insert process means I have the first component, just here. And then for the second component, I just manually insert it on the cavity and just overmold the second one. So to see the optical properties, I analyzed the residual stress inside of the polycarbonate. And here you can see I work with the polarization microscope from Carl Zeiss, and to see the birefringence of my component. Then afterwards, I did the annealing by 120 degrees for 96 hours. All of these process parameters, I did the research before. I'm just not going to tell them. Yeah, so what is the cause of birefringence? We have residual stresses and molecular orientation. Molecular orientation, I can do better or worse in the process, but the residual stresses, I can also work afterwards with them in the time I do the annealing. What I have at the end, it's going to be only the molecular orientation and not anymore the residual stress. So for just to have an overview, what I did is For the birefringence for this polarization microscope, I have 6 points. It's important to see that here is the runner of the first component. Then I have 1, 2, 3, 4, and then on both sides. And for the contact surface analysis, I just cut between the runner of the first component and the runner of the second component in the cut A, and that's what I saw in the microscope. So for the isothermal injection molding, I was just showed the best and the worst scenario, because in the time it's a lot of diagrams. So I have a best scenario in the isothermal injection molding is when the melt of the component is high. It's high for my standards. It's 320 degrees. And the worst was when the injection velocity was 5 millimeters per second. This is why, because when the melt temperature is higher, the fluid is going to be fluid. Yeah. So it can go better into the cavity and go around it. And for the slow injection molding, for the slower injection velocity, it can result to a lot of residual stresses because of the cooling rates, and it's more severe to cooling gradients. So what I did is I have here what is the isothermal injection molding that I just showed in comparison with the annealing after the 96 hours. What we can see is the annealing actually improve my birefringence in almost 38% of the birefringence. And then we have here the baryothermal injection molding. Here I don't have the same results. Like I don't have the same best and better and worst scenario because of the temperature as well. That I have the baryothermal injection molding. So here actually I have the best and the worst. I have the holding pressure for both. The lower holding pressure was the worst case, and the highest was the best case. Here it's also because of the baryothermal process, which also the temperature is higher, so my component is in the other one hotter, so it fluids better. Again, in comparison with the annealing, yeah, thank you. Here I also saw 53% better improvement. So it's better to do baryothermal and annealing. So here again, it's isothermal and baryothermal in annealing, which baryothermal is 30% better than the isothermal. So I'm almost going to finish. The last part is the results and discussion of the contact area. I have you can see here the two components, and I know it's not good to see, but the line here should represent the surface contact. So I'm just going to zoom of the two worst case scenarios, and I have the holding pressure by 300 bar, which is low, and I have the melt temperature by 280, which is high. In the moment when it reached the second component, the component that it's already done. So why is that? I can say that the holding pressure, if you use 300 bar, the glass transition temperature, it's going to be lower than if you use, for example, 800 bars. That means if it touch, it's going to make a diffusion, but it's going to also alter my contact surface. And in case of the 280 degrees, is that I cannot see it here that it's below, but from the PVT behavior of my polymer, I can say that if I have a lower pressure, my temperature, my glass transition temperature is also going to be lower. So that's the reason why it's, yeah. And to summarize, barothermal annealing is barothermal in work with annealing is better for my optical properties of the injection molding. And in case of the surface, contact surface, I have to see that I don't have too much temperature or too low pressure. Thank you very much.
That was a long presentation.
I did 21 minutes.
You have 15 minutes to do that.
In the webpage said 20 minutes.
It's 15 minutes.
It says 20.
It says 20 minutes.
20 minutes.
You can check the program, it's 15.
No, it
No,
says,
it's
it says
20.
Which program?
25 years.
Yeah, I'm just looking here and I'm like, I haven't been here that long.
Yeah, okay.
Now it's okay. It's okay.
So can I ask question?
Yes, please.
So the maximum birefringence that you measure is around 10 to minus 5.
Yeah.
And I'm trying to understand if it's too much or it's okay. So mostly these lenses are used with non-polarized light.
Yeah.
So is it really important to have it? Is it a problem?
It is a problem because the light is going to be diverted. Actually, the thing is,
For non-polarized light.
yeah, for non-polarized light. But the thing is, I'm now, this is like I'll call it basic research. So yeah, so I'm doing it's only a lens at the beginning. Then afterwards, maybe for the part that
For more sophisticated.
yeah, exactly. If someone wants to, it's so we can know all the optical parameters that I can present. Yeah. So do you have any more questions?
Why?
Question? Yes, of course.
Why do you resist your materials to PMMA?
PMMA, yeah.
And polycarbonate. You know that polycarbonate is very transparent.
Yeah.
I don't know why you are using PMMA.
PMMA is also really transparent. This is what's called plexiglass, which is, yeah.
And you are talking about that you have this property materials.
Yeah.
I'm thinking that why not doping this material with some other materials like other materials?
Yeah, this is, as I said, it's a really main basic research because there is the gap that it's about achromatic lenses. There is really no research about combining two transparent materials for optics. Yeah, so I think this is like the beginning of it.
All right, thank you. I
Thank
think
you
then we
very
can
much.
collaborate. Talk more.
Yeah, of course.
This is certificate. Can someone
Wait,
just take a picture of her?
Yeah, wait. So, okay. Yes, can someone take a picture? Joe.
You're calling me.
Yeah, so just you're weak. Thank you very much.
Thank you.
Thank you.
I call on okay, as they are presenting this certificate here, just give me 1 minute. I will call on Sweta Madamala from MBJ College of Engineering, India. Please, your time starts now. You can start presenting. Thank you so much. You're there.
Where is the presentation? Presentation.
File.
Already sent you.
నాకు సెండ్ చేశారా నా ఈమెయిల్
యూకే ప్రెసెంట్
ఇదేనా
ఓపెన్ చేయండి.
ఇదేనా కాదా ఈమెయిల్ అయితే నాకు రాలేదు అంటే పర్సనల్
స్కాలర్స్ అని పంపించానండి. స్కాలర్ కాంపిటెన్సెస్
her file in her pen drive. A file in her pen drive. Also,
Good afternoon to one and all. So this is Shweta and I'm from India. So before starting this, I would like to tell a few words regarding about my studies and all. So I did my bachelor's in BSc Biotechnology. Then I did my master's in organic chemistry. Then I did my PhD. So last year only I finished my PhD. So recently I awarded as a doctorate. So and this is one of the part of my PhD studies only. So that I am going to explain you now. And the topic, title of my topic is in vitro cytotoxicity of ursolic acid, 6-methyl bromohydrate, and germanic acid. So based on all these are the plant materials. So now I am dealing only the herbal chemistry or herbal medicines we are taking. So general medicinal chemistry, it will come under the medicinal chemistry. So in that we took the 3 different plants we collected. So in that active plants we are active constants we isolated. So these are the 3 active isolants from the plant materials. So one is ursolic acid, another one is on 6-methyl bromohydrate, and finally third one is on germanic acid. So based on these plant materials, I did the investigation on biological applications. So that is about the breast cancer. That is one of the disease space we are facing in the world nowadays. Particularly, so this is the MCF7 cell lines and A549 cell lines. I took these 2 cell lines. So and based on these 2 cell lines, I did the comparative study and investigations also. I had done. So next, coming to one title, that is a science maybe set the limits to knowledge, but it should not set limits to the imagination. So now we'll start our presentation. So these are the contents, the flow of our PPTs will be go on. So introduction part, selection, techniques, development, and biological application. So coming to our herbal plants. So herbal plants, already you know that herbal plants means which will be, there is a lot of history in the herbal plants bio issues. So in this herbal plants, there are different herbal plants. In our home only, so many plants are there, which will be very beneficial to us. So few may know about the benefits of that and few people, they don't know the benefits of that. So it may be useful, it will be useful for the so many diseases. So herbal plants have been identified and used throughout the human history, and plants make many chemical compounds that for the biological functions, including the defending against the insects, fungi, as well as the herbivorous mammals. So if you take the plants means in or around, there is a 12,000 such compounds have been isolated, and these are estimated only less than 10% only we have estimated, and we are using for the research side. So I hope now we are more concentrating on the herbal plants instead of the novel plants. Why? Because novel plants, it will give an instant relief to you. When you take for the herbal plants and all in a dosage form, it will interact, it will affect to the patient slowly, and but the results will be surely results will be a good results, and definitely it will cure the particular diseases and all. So here, chemical compounds in the plants may mediate their effect on the human body. Through the process, we'll identify identical dose and understand for them the chemical compounds. So about Indian herbs and all. So while pharmaceutical companies, so I already told this point, while pharmaceutical companies extract active ingredients from the plants and they sell them as a drug form. So now what we are doing means, so instead of Ayurveda is there, so Ayurveda, not we are completely going for the Ayurveda. Now we are isolating the plants. We will take different parts of our plants. So in that different plants, we will extract the main active ingredient. So with that ingredient, we are going to develop a method. Then we are applying for the various parameters. Then we are going for the studies, that is the biological studies we are doing. So in general, herbs and plants are used as a flavoring for the food, medicine, perfumes, and these are called as the herbaceous plants. So and they have a variety of uses like as culinary uses, medicinal uses, and spiritual changes also as there. And these are the various points which are regarding about the medicinal plants. So some will be used as an primary metabolites, and some plants will be used as an secondary metabolites. And in most of India, we'll use all the medicinal plants which are cultivated from in around our country. And among them, there is a great demand abroad. Even in abroad also, we have a great demand on opium, cocoa, tropane, alkali bearing plant materials. And Indian system of medicines. So these are mostly finally used for the therapy against many diseases like jaundice, asthma, and diabetes also in India nowadays. We are not nowadays. In olden days, if you take the history of India also, they are used to cure all these diseases. So India has 2,000 species of medicinal plants as there, and which has a vast geographical area with a high production and having an agricultural conditions also. And this slide is mainly representing which I opt for my studies, or we opt for my studies. I means only I will come, and we means me and my guide will come including in this. So we opted for the 3 plants. So one is Morinda citrifolia, and other one is Alges marmolus, and third one is Gymnema sylvestre. And the scientific names are, these are the 3 scientific names. These are the common names which you generally will call it. This is a noni fruit, which is famous in Chennai and all. And bay leaf, which is used for most of the Indians, they will use this leaf or a plant. In that particularly, we have selected the leaf plant, which is used for the puja of Shiva, Shivaling and all. They will do this puja with this leaf only. And Gymnema sylvestre, this is an Australian cow plant. So this plant is used for the treatment of diabetics. So all these are having in various benefits, various properties to cure the various diseases. Now we are combining these 3 materials. So in these 3 plant materials, we will take the active components, and we are developing a method called HPLC method. So high performance liquid chromatography technique. So in this technique, we developed an optimized method. Then we go on for the various parameters also. So after isolating the 3 components, so these are the 3 marker compounds we have identified. One is 6-methyl bromohydrate, ursolic acid, and gymnemic acid. So based on the literature survey, we have identified that these 3 plants is when did the research on only diabetics. Now we are going for the another step, that is these 3 plants we can use for the anti-cancer treatment also. It has a property of anti-cancer treatment. So that we are going to do. So by which method means we are going for an in vitro, that is MTT assay. We are doing that for biological activity to prove the anti-cancer property. And this is a protocol or proliferation or which we can do for the MTT assay. So MTT assay is nothing generally. It is used to measure the cellular metabolic activities. So that is called as MTT assay of cell viability and proliferation and cytotoxicity we are going to do. So in which method, which instrument we are going to take means here calorimetric method we are taking. So it is a method where it is based upon the reduction process. So by using on this MTT assay, we did the cytotoxicity effect of our 2 cell lines. One is A549 and MCF7 cell lines. And these are the measurement, how to measure the cytotoxicity and all. So based on a few examples and proliferation kit, we have did this experiment part. And coming to the method, so in which method we have done means here in vitro cytotoxicity, we have taken the standard one. So that is standard gymnomic acid. Along with that MS extract we have collected, and MS extract of human breast, that is MCF7 cell lines and A549 cell lines. You may have a question that why we opted of two different cells. So based on the, I told you that comparative studies. Now in one stretch, we are doing the comparative studies of both the A549 and MCF7 cell lines. So these two are the cancer causing cells. So based on this standard gymnomic acid, now we are doing this MTT assay. So for this test, we have cytotoxic studies. We have collected the 10 mg of test substances, which were separated based on the resolutions. And a volume is made up of an MEM supplement. So with the 2% inactivated FBS to obtain a stock solution of 1 mg per ml concentration. And we have given the injections also, which is sterilized for that, for the filtration purpose. So after doing this and all, so we have identified that. So based on the conditions like, so we are incubated at 37 degrees for 72 hours with a 5% of CO2 carbon dioxide atmospheric pressure with a stretch of 24 intervals. So we noticed that as we are keep on increasing the concentration of our standard solutions, so the cytotoxicity is also gradually increasing. So with having an concentration of 62.52 and 1000 ml per 1000 micrograms per ml, we have drawn the graphs also. So which is, so these are the graphs. So where we can see that if you are keep on increasing the concentration, our cells also, the cytotoxicity of the plant material, whatever we have taken the standard plant material, gymnomic acid, keep on increasing. So and it is not exceeding that, which is beyond 1000 ml, it is not exceeding. Below that only, it is increasing its cytotoxicity. And this slide is particularly represent that I told you that we did the HPLC technique, and this is the chromatograms where we can see that technique and all. So based on this technique only, we have gone for the next step, that is the cytotoxicity effect, cytotoxicity. And this is the representation, and first figure is representing the morphological changes of MCF7 cell lines. So this is then our reviewers. So which is on a base paper we have taken. So based on this base paper, we have gone to our final, this is our results based on our plant materials. We got these cell lines. So if you check these cell lines, initially it is the control, and this is the A, B, C slides. So from A to I, if you take means, if you increasing the concentration of your, whatever the concentration we have taken, if you keep on increasing means our slides also, or the cells also will show the variations. You can see the cytotoxicity effect easily. So it will also increase, and it will not go beyond the whatever the concentration we have obtained, that is 62.5 to 1000 mg per liter. So which is in between this range only our concentrations will be there. And this is an anti-cancer assay after doing the cytotoxicity, and how you will calculate means based on this anti-cancer assay we will calculate. And this is the formula: stimulation by index will that is equals to absorbance with the plant extract by absorbance without the plant extract. If you do this, we will get the anti-cancer assay. So based on that, we did the cytotoxicity results and all. And coming to final discussions and conclusions, the test sample, whatever we have collected, that is standard gymnomic acid and MS extract, were tested for the in vitro studies. So if you see on this, the test substances were taken at the concentrations ranges from 1000 ml to 62.5 ml to determine the percentage growth. So it's keep on increasing, that is below, so less than 1000 mg per micrograms per milliliter. So this is the results, and this is the discussions and conclusions. And these are the test results based on the cytotoxicity. So if you see the table 1 cytotoxicity property, which is dependent upon the MCF7 cell lines, and this is an A549 cell lines. In both, we can see the cytotoxicity. So it is keep on increasing from 1.62.5 means 1, and 125 means 3.5, and 250 means 19.5, and 500 means 22.83, whereas 1000 means 30.03. So keep on increasing our test concentrations.
our cytotoxicity is also increasing. So which is not CTC 50, if you take means which is below less than 1000 only. So these are the references. And finally, I acknowledge my university, that is JNT University. And I would like to thank to my professors also, Dr. Sarita and Professor Devanasar, and with the continuous guiding and all. And I thank my institution, so that is MBJ College of Engineering. So they promoted me to come and present here at talk. So thanks for giving me this opportunity. And not but the least, I will thank to the Scholars Conference also. So they gave an opportunity to present here. At last, I would like to thank my parents, that too particularly my mother. She, without her support, I cannot come here also. So thank you so much for giving this opportunity. Thank you.
Any questions for her?
I just want to ask whether when you did the activity, was it on the extract or was it on the pure compound?
Ma'am, we took the pure component as well as the extract also we did the studies. With the pure and pure one and extract also we have to do the studies. Without pure one, we cannot do this.
So you mean the pure one because you purchased it?
Yes.
But you didn't try to extract the pure the active
No,
ingredient
we
from
did the
plant?
comparative studies with the standard one as well as our extract. Like that we have to do. Thank you so much.
Right. Any other question? Yes, yes or no? Any pictures? Thank you. Yes, we call them, huh? Presentation, Kiomea Lao Lu. Hope I call it well. Pardon me if I didn't pronounce your name well. She's from the University of Mauritius. Mauritius. Structural biological and catalytic activities of different sulfite derivatives. She has a personal chair in organic chemistry at the University of Mauritius. Is recognized nationally and technically for her research contribution and achievement in organic and surfactants chemistry, and also organometallic products. She is also interested in forensic science. She has published over 80 articles, papers in peer-reviewed journals.
Just remove the slide. Can you hide it?
No, it won't show.
Okay, thank you.
Click like this. Okay.
Okay, good evening, everyone. I'm Sabina from Mauritius. My talk today is going to be on biological activities of diphenyl disulfide derivatives. Now, when I was talking to members in this conference, someone asked me, where is Mauritius? So I'd have a picture for Mauritius. Mauritius is a very small island, and we have got a population of around 1.4 million people, and it is in the Indian Ocean, but it is one of the pillars of the economy is the tourists. So we have got many tourists from over the world which come to Mauritius. And these are some pictures showing the picture of Mauritius. We are known for the beaches, and the temperature of Mauritius ranges normally from 25 to 30. That we get 32, 33 like it is the most. So we don't have extreme temperature really. So here I feel very quite cold in England for the time being. Okay, so this is like the seven-colored earth. I think it is unique in the world. I think that there's not many places that you have got this. And these are some pictures of my university. And my talk is going to be arranged as an introduction about the aryl disulfide, some metal frameworks with sulfur functionalities, metal complexes with disulfide, benzoates, and from diamines compounds. Now, to start with, disulfide scaffolds are important motifs because of their unique pharmacological and physical chemical properties, and they are found in protein structures. You can also find them in natural products, for example, polycarbamide, You can also find them in a number of pharmaceuticals, for example, Istadax, which is used as an anti-tumor agent. And you can find them in number of food chemistry. For example, you have got in allicin and ajwain, which is used commonly in the Indian food. And it is also used now as the linker is used as an attachment to deliver active drug to target cell. Now, diaryl disulfides are very interesting compounds because they have the versatile biological properties. Recently, there has been the plural and the bromo derivatives have been found to have anti-tumor properties and anti-cancer properties. Similarly, we have got that they can also show anti-corrosion capacity. Like Tan in 2020 reported that the diacid and the diamine act as corrosion inhibitors of copper in acidic medium. Now, these disulfide diaryl compounds in the containing the acyl and imide groups have also been reported to show photocytotoxic activity against common species of weed found in common rice and cereal crops. The diamine and the imines derivatives have been found to show a number of antimicrobial properties. And for example, the diamine and the diaryl sulfide ship bases have shown antibacterial activity against the multi-drug Actinobacter baumannii. And these disulfides are also known to interact with DNA and BSA. Now, in our group, we have synthesized a number of these diaryl disulfide compounds. Now, because in this, here we started with a diacid and we have introduced long alkyl chain. So we have converted these diacid into surfactants because in the alkyl group, we are having more than 8 carbons. And we find that from X-ray, we find that these compounds, these disulfide can be stabilized by the CHO bond and also from the sulfur pi interaction. And this type of interaction is known to be significant also in biomolecular systems. And because I said that these can be classified as surfactants now because they have got more than 8 carbon, we determine their critical micelle concentration. And here we use the Parine as fluorescent probe because these surfactants that we are determining was neutral in characteristic. And we find that as we increase the alkyl chain, there was a decrease in the CMC value, which shows that there can be enhancement in the ease of micelle formation. And we determine also the antibacterial activity of these compounds, and we find that the one which was having C12 alkyl chain was showing highest activity. And what was also very interesting for us to note that when we compare the MIC value, that is the antibacterial value, with the CMC, we find that the antibacterial activity was mostly governed by the monomers rather than their micelles. We also synthesized another series where instead of using the diacid, we had used the diamine. And here also we got the same result for the CMC value. And with this series of compounds, we also studied the binding studied with BSA. And as you know that the serum albumin is important in binding, transport, and delivery of drugs around the body in the bloodstream to target these destinations. So we studied the BSA binding properties, and here we use BSA as the model compound for the serum albumin because this is quite cheap and it resembles the human serum albumin by 76%, and it is stable. And when we did the BSA binding studies, we used the fluorescence spectroscopy, and we find that an addition of our diamine in disulfide with BSA, there was a decrease in the fluorescence intensity, showing that our BSA disulfide complex was non-fluorescent. And we studied the which type of quenching mechanism our disulfide were having with the BSA, and we find we find it with using the Stern-Volmer equation, and we find that the KQ value was in all the cases here, it was greater than 2 times 10 raised power 10, which is the reported maximum dynamic quenching. So this implies that our compounds were having mainly static quenching mechanism rather than dynamic mechanism. And we also find the Ka value, which gives an indication about the plasma distribution of the compounds. And we found again here that at the C12, when the compound was having a C12 alkyl chain, and we have got a highest Ka value. Close this one. Sorry, right. Okay. Maybe because of this screen, I find double screen on the computer. I think okay, it doesn't matter. So I think I should have gone back. It is. How should I go back? Now, when we were studying the fluorescence studies, so we also find that because when we did it with different thermodynamic parameters, we find that the free energy was all negative, implying that the BSA disulfide complex occurs spontaneously. And also we found that the enthalpy and the entropy value were less than 0, indicating that the interaction was enthalpically driven, but entropically unfavorable. And because both values were less than 0, from the literature, we can conclude that the disulfide interaction with BSA were mainly via van der Waals and hydrogen bonding. We also studied where does these molecules bind with the BSA, and we used the site markers. 2 site markers we have used, warfarin and ibuprofen, to know where it is binding. And we find that when we added our compound, we find that there was a decrease in the Ka value, which implies that our compound was competing with both warfarin and ibuprofen, showing that there can be interaction at both sides. We also synthesized a series of the imines disulfides, and we find from X-ray and both X-ray and spectral studies that these compounds exist mainly in the enol tautomerism. And we studied the biological properties of these compounds. And in these compounds, we have replaced one of the hydrogen on the benzene ring by T-butyl ring. And we find that when we put T-butyl ring, the activity increases, but the position of the T-butyl ring did not really influence either the antibacterial or the antioxidant properties. Now, the next part of my talk is going to be on metal complexes of disulfide. Now, we know that disulfide metal complexes can have monomeric, dimeric, or polymeric compounds. Now, we can have coordination of metals with the diaryl disulfide with no cleavage of the sulfur-sulfur, with no sulfur coordination, and with no cleavage and sulfur coordination, or we can have cleavage of the sulfur-sulfur, then monocoordination, or forming tetra or bidentate type of ligand. Or we can have either extrusion of sulfur, or we can also have insertion of sulfur prior to coordination with metal. Now, the first ligand that we started was the dithiodibenzoic acid. Now, dithiodibenzoic acid is a multifunctional ligand containing both the carboxylic and the thi groups, and it can be twisted around the carbon sulfur or a sulfur sulfur bond, and it can undergo reaction such as oxidation or sulfur sulfur bondation prior to coordination. And when we take this ligand, we couple it with nitrogen and donor auxiliary ligands, these can form a number of frameworks with interesting topologies. So the first part of the metal complex that we had is we had taken diacids. We could observe there could have been cleavage, there could have been no cleavage with monocoordination, bidentate formation, or there can have been extrusion, or there have been oxidation and then coordination with metal. So we did the reaction of the dithiodibenzoic acid with palladium chloride acetonitride under 2 different conditions, that is the classical method, just sort of the refluxing, or we did it also with slow diffusion. And we found that in the first series here, we have different complexes And the structures of these complexes were confirmed by spectral and X-ray studies. Now, for example, like the palladium one, there was reductive of sulfur-sulfur, and then the thiobenzoate anion coordinates to the palladium atom via the carboxylate, oxygen, and sulfur, and forming square planar complex. In the palladium 2 and palladium 3, we have the same type of complex, but what we found also is there was unreacted dibenzoic acid, which was encrusted in the tricyclic system. Now, we did the same reaction with ruthenium trichloride, and we got a completely different structure. So you can see the slow diffusion here. It was in DMF and water, and these are how the crystals were forming down. You just have to leave it. Sometimes it takes like more than 1 month to get the crystals back. And here again, in this case, we find that there was sulfur-sulfur cleavage, and followed by oxidation of the new sulfonito benzoate ligand. So this was not a common thing to observe, but we confirmed the structure by X-ray. And the ruthenium was found to be a hexacoordinated and reside in a distorted octahedral ON4S coordination geometry. And what was more unusual here was that normally you have got the oxygen, normally the metal ion was coordinating here with the sulfur atom rather than oxygen, which was normally the case. And here the carboxylate was monodentate. This could be confirmed both by IR and by X-ray studies. Now, we did also the reaction using copper chloride, and I think you can see the crystals here forming in the test tube with slow diffusion. And here again, when we use different nitrogen auxiliary ligand, we get different complexes. So when we use phenolphthalein, pyridine, and bipyridine, we had got the CU1, CU3, CU4. And in this reaction, what was also interesting is because here we had observed extrusion of sulfur, and that sulfur in the same reaction get oxidized to sulfate and coordinate with the metal. But we'll say that we didn't find the same observation when we use pyridine. So these are the metal complexes that we were talking about, CU1, CU3, CU4. And we have got like the disulfide clay, there was extrusion, and then there was metal-metal coordination. And also the metal-metal, there was no bond between them because the distance was longer than the sum of the van der Waals forces. And as I said, that after extrusion of sulfur, the sulfur get oxidized to sulfate, and we got these two complexes when we had phenolphthalein and bipyridine as auxiliary ligand. But as I said, there was no such complex was observed when we use pyridine, because we assume that maybe in the presence of copper sulfate, the pyridine got oxidized to pyridinones. Now, as I mentioned, we also synthesized a number of Schiff bases, which I have already explained the biological activity, but we also did the metal complexes, where we find that we could obtain the complexes form was either mononuclear, binuclear, or polynuclear, depending on the reaction condition used or the metal salts used. So when we did it under refluxing condition, we got no cleavage of sulfur-sulfur was observed, whereas when we did into slow diffusion, sulfur-sulfur coordination, sulfur-sulfur cleavage was observed to give us different types of complexes. So this is one of the complexes which was formed after cleavage. And again, here there was no copper-copper interaction was observed. So we have a polynuclear complex which was formed in this case. Again, here it was another Schiff base which we synthesized. And in this case, there was cleavage of sulfur and then coordination with the metal. We did the metal of palladium and copper, where the metal was in a square planar, in a trident, square planar type of distorted square planar geometry. And when we use palladium chloride, we got, there was sulfur-sulfur scission, but we got a tetranuclear complex. And also when we did ruthenium also, we had a tetranuclear complex or a polynuclear complex was obtained. Now, we have been studying the biological properties of these ligands and metal complexes. And in all the cases, we found that the disulfide ligands, the ligands were more active than the carboxylate anion first. And also the metal complexes display more inhibitory activity compared to their respective ligands. And also, we found that because when this could be explained either by the chelation theory or by the enhanced lipophilicity character that is of the penetration of the complex into the lipid layer. And these are some of the results of the radical scavenging activity. And we found that the metal complexes were having lower IC50 value, that is higher antioxidant properties or radical scavenging activity. And we can also find that when the metal complexes had a free OH, that is the OH was not coordinating with the metal, it was showing better radical scavenging activity. So you can see in these two cases where we had got the OH, it was free, it was not coordinating, it was showing better activity. We also studied the binding study with DNA. Now, the molecules normally interact with DNA either via electrostatic or hydrogen bonding, and it can have either intercalation, that is instead inserted in the DNA, or it can have groove binding or surface binding. Now, when we did for our compounds, two examples here, with SbCu3, we find that there was an increase in absorbance, suggesting that the complex binds either via external contact, that is surface binding or groove binding. And whereas when we did for SbCu4, there was a redshift and there was a decrease in absorbance, which shows that it may have an intercalating mode of interaction with the DNA. And we also did some experiment with plasmid DNA, and we found that this was the shift base, one of the shift base that we have used. And these are the metal complex which I have already discussed. This is the pure DNA. So this is in the form 1, which is the plasmid DNA, which is a circular. So when we did the compound, suppose SbCu4, SbCu3, and SbCu2, we find that it converted the supercoiled DNA into form 2 or a form 3 DNA, which was linear, that is, was cutting the DNA. So to conclude, we saw that the diaryl disulfide can possess flexible sulfide spacer groups between two aryl rings, and they can coordinate with metal either via cleavage or non-cleavage of sulfur, oxidation of sulfur, or insertion of sulfur, giving rise to different types of topologies. And these compounds can also show very interesting biological properties. These days, I'm working on metal complexes of other disulfide ligands containing other functional groups with long alkyl chain. And I'm also, my work is also based on amino-based surfactants. And I have just had one paper on DOPA derivatives, which has just come out, which I've just published. And I would like to acknowledge Dr. Huston and Dr. Coase for doing the X-ray of the different metal complexes, and my colleagues, Professor Bowen, who is an inorganic chemist, and Ashley, Professor Kamal, and the two PhD students who has worked on this, Dr. Musen and Dr. Junberg. And I'm also the Department of Chemistry and University of Mauritius, and I'm also grateful to the Chemistry Frontier 2023 to give me the chance to present my work. Thanking you for your attention.
Any questions? Yes, it's none. Anyone thinking? Are we calling on them others? Sherry Man from Westman Institute of Science, Israel. He is an academic researcher from Westman Institute of Science. The author has contributed to research in topics such as nanowires and electrons. The author has the 8th index factor of 55. He has co-authored 237 publications, receiving 14,819 citations in various affiliations from others. Sherif Man include the University of Cambridge.
But how do I close this and how do I?
Where's the part?
I need these.
Did it
No,
right?
no, this is the talk. It's okay.
Yours, right?
Yes. It was right there. I'll do it. I'll do it.
This is a talk, right?
Yes, just press twice.
No, maybe we try nobody on wait. Okay, let's do it your own way. Do it your way.
Yes, just. It was open already.
Maybe it's there. Where?
Wait. Where?
Okay.
Ah, yes. And now I have to close this side.
That's what I'm saying.
That's what are you saying? Maybe. Wait.
Got something there.
No, here, this one. What? No. Ah, these are the recordings. Oh my God. Somewhere here is the, somewhere here, down here, is exactly what I need, but I don't know how to remove this. Eli.
We need to call the experts.
לא, זה עניין של מה בכך.
That's what I'm saying. If you close from here, let's close this one.
Close which one?
This one. Close this one. We come back here. The one we did last time, open it with this one.
But it doesn't want to open.
With someone to.
Ah, here. Okay.
Actually,
And
we need the expert.
And yeah, how can you?
Here. Okay, so now okay, hi. So I'm gonna tell you I need a pointer. Somebody wants to give me a pointer. Thank you. So I'm gonna tell you I call my talk The Curious Case of Europium and Indium Arsenide, or the fascinating crystal structure of Europium Indium Arsenide shells on Indium Arsenide nanowires. Thank you. Oh, lovely. Okay, so and to move back and forth. Oh, good. So the outline of my talk. First, I'll give you a short introduction to the growth of reclining nanowires on the 100 because it's not a trigger process, and then I'll tell you about the growth of shells of Europium indium arsenide on woodside indium arsenide, and how they grow the same shells on zinc blend stalactite, so-called stalactite nanowires, which introduced the necessity of growing zinc blend indium arsenide antimonide nanowires as the core, instead of indium arsenide, and we did some squid measurements. So this is my MBE system, and which is a classic reverse system, and this is how we grow. We evaporate. So there was an introduction before, but we evaporate a very thin layer of gold, 1 nanometer, in situ in a chamber that is hidden around here. And upon heating, we get the droplets on the surface, and by evaporating the necessary materials, the droplets get to supersaturation, and they determine the diameter of the wire, and the time determines the length. Okay. Sorry. So, and we can grow on various substrates. This is an example of indium arsenide. So on 111, what determines is the arsenic dangling bond. They will follow the direction of the arsenic dangling bond. So on a 111 substrate, they will grow vertical. On a 001 substrate at around 60 degrees to the surface. As you can see in these two surfaces, which are, this is 001, and this one is 25 degrees tilted from 001 towards the 111. So you see kind of craters. And now I'll tell you briefly what these craters are. So we focus mostly on this 100 growth, where the advantage is, first of all, that the wires grow tilted at 35 degrees to the surface. And so for some evaporation processes, the large surface area exposed to the beam is an advantage. And also, since they grow along both 011 directions, they can merge and form intersections. So as you can see here, in order to grow wires on the 100 surface, we first have to form a 111 faces, from which, like on a 111 surface, the advantage of growing on 111 is the large surface mobility on 111. But you can see that in order to be able to grow on 001, first 111 facets need to form on the surface, and this is how they form. So initially, the gold is there as small droplets, and during the growth, first, this crater structure forms, and you can see by this AFM that it really has, indeed, it has a depth, and also in this cross-section, and only when the gold droplet is well situated on the facet and the collection area is large enough for the droplet to obtain a supersaturation, a wire can grow from this particular facet. So here you can see just two accidental craters, one top view and a side view with the respective facets, and the wires will grow only from the 111 facets, and this is why it's nice to grow on these wires where on this surface where the wires can merge. This is an example for this advantage. You can see on the same growth in the very same conditions that this wire grew vertical to the substrate, and these two wires are reclining, and for in situ aluminum coating, where there is intimate contact between the aluminum and the indium arsenide wires, you can see that the vertical wire ended up with the aluminum balling up and where the aluminum maintained its continuous coating on the reclining wire. We're all aluminum, for example, is important for forming hybrid devices for example, for observation of Majorana particles, and one of the other materials that is necessary is what was suggested by the group in Copenhagen, who applied the magnetic ferromagnet on top of the magnetic of the between the wire and the superconductor in the form of europium sulfide. And lately there is much interest in the materials that contain a rare earth atom such as europium, and this family of materials is called the rare earth zintal phases, and they are composed of a 3,5 materials such as indium arsenide, indium phosphide, all this family of materials with a rare earth, and the europium introduced into indium arsenide has been suggested as a interesting material for forming an antiferromagnetic an axion insulator with antiferromagnetic long-range order. And so we saw this and we thought it would be interesting to try and check what happens when we introduce europium into our indium arsenide wires. So we had the courage of introducing europium into the MBE system. And initially, we grow what we knew best, and that was the indium arsenide, Wurtzite, reclining wires, okay? And we try to grow on them in europium indium arsenide, hoping that the indium arsenide will serve as a stem and they will grow along it, on top of it. But what we found is that they form shells, and not only shells, these ugly shells. So this is the europium, the indium arsenide core, and this is the europium indium arsenide shell that grew on top. But what we noticed, we need some dark. So how to do it? We need some lights on oil.
One of the other ones.
First one, the first one.
Yeah, it's good. It's okay. It's okay.
Okay, so what we noticed, and I hope you can notice this, is this very peculiar structure, which is kind of zinc blende-like, reminds of the zinc blende, but not quite. And this EDS shows you that the europium indeed got into the shell. So this is the indium, the arsenic, and the europium. And because of this strain and the mismatch between the europium and indium arsenide, and then you see some curvature of the wire. But the surface was very, very ugly. So this is another example. This is kind of a top, it's not a top view, it's a 45 degrees top view. And so you see there is some structure on the shell. And this is the lamella made, TEM and EDS of a lamella cut in the wire. So this is the indium arsenide wire. And this is this shell showing that it has the europium, the indium, and the arsenic. So now, where the wires are very dense on the sample, they merge easily. And when they merge, there is high chance for this what we call stalactite wire that forms at the intersection. So the gold of the two wires merges and it splits, and some of the gold gives rise to a wire that doesn't grow like the initial Wurtzite wires, but forms a wire growing perpendicular to the substrate, namely it's zinc blende, and it's 1,0. It's growing into the 1,0,0 direction, and thus it must be zinc blende. Okay, and then so we looked for these wires, and what we noticed is that these wires are very smoothly coated, contrary to all these wires that the Wurtzite wires that, as you see here, are very ugly. So here is another example. You see the coating on the Wurtzite. This is Wurtzite, and this is all Wurtzite. The coating on the Wurtzite is very rough, and the coating on the zinc blended wire is very smooth. So we studied these few wires that we could find and locate on the sample, and we saw this very, very intriguing structure that is kind of zinc blende like. It's not the zinc blende as you can see here, but it's similar to the zinc blende, and it has these planes, parallel planes in these two directions. It reminded us of this work on cadmium telluride grown on indium antimonite, for example. This is another example showing also the EDS. So this is a Hadaf image of such a wire, and you see that the europium goes into the wire but accumulates below the gold droplet. This is the gold that remains there, arsenic. As you can see, arsenic does not really enter the gold droplet, and the indium that is everywhere. So we looked in a high resolution Hadaf, and what we saw is this. Here you can see an extension, a higher magnification of this peculiar structure. And what we saw is that the europium atom is connected to has an octahedral coordination connected to two arsenic atoms and the two indium atoms on the other side. Namely, there's a inversion domain boundary at the europium plane, which inverts the structure. And so from both sides of the europium plane, you have arsenic, indium, arsenic, indium, arsenic, indium. And so this was very, very stunning to us. And then we decided that it's worth studying. So to begin with, we needed a lot of wires. It was not enough to find one here and there. And so we decided that we must learn how to grow those shells on zinc blended wires with a large density. So we just added a little bit of antimony based on well-known works that were published a long time ago. So if you put a little bit of antimony into the indium arsenide, the structure will change immediately from Wurtzite to zinc blended. And so we could grow a very high density of zinc blended wires that had a little bit of antimony inside. It didn't matter. So now the same europium indium arsenide, and so we got a high population of quite smooth coating. And as you can see here, this is the coating and this is the wire. You can see the same intriguing structure of this zinc blended like on the side. here the EDS, the chemical composition, you see there's the europium in this shell. The antimony is mostly in the core. Indium, arsenic, this is the hadaf of this lamella. And the composition, we could push it to 12%, to 12 atomic percent. This is this demonstrates the difference between the coating of this shell when it's situated on the zinc blende part of the wire, and all these wires, I mean, most of these wires, we can grow the indium arsenide and timonide directly on the indium arsenide or on a stem. So in this sample, for example, there was an indium arsenide stem. So it's nice to compare the position on the indium arsenide, the woodside stem, and you can see in the TEM how the material actually prefers to deposit on the zinc blende. And so our colleagues in Poland who would use the molecular dynamic simulations and other methods simulated this and showed that the europium really likes to sit more on the zinc blende than on the wood side. The parameters they changed were temperature, cooling rate, and the side facets of the core. So it was obvious also from theoretical considerations that the europium will want to sit on the zinc blende. Here is just a nice picture that I like because it demonstrates the various types of wires. The shell is still this europium indium arsenide. Here you have a twinning superlattice that grew initially. The indium arsenic antimonide has a tendency of forming twinning superlattices. So this one had a superlattice in the core. Here you see nicely the difference between the wood side and the zinc blende. Here you see a single twin plane. And here again, the zinc blende core coated by europium indium arsenide, which is very smooth. And this one very rough, where it's wood side. More of these EDS mappings, and so the mapping, this is the EDS shows you how the europium is situated. This is the high magnification of this zinc blende structure, and here a small section of it. When we collect all the EDS data, we find that the arsenic maintains its 50%, and the europium takes the place of the indium only, and not the place of the arsenic. And so, this is another nice picture, and what you can notice here is that we were intrigued by these elongations because, as you have seen, the europium planes form, as you can see over here, forms a phase boundary. And so we asked ourselves, if the lattice flips along this plane, maybe somewhere else it flips back. But what our microscopist Lothar explained to us that this does not happen, and these elongations are actually the plane that is lying below. I will explain and show you. So as you can see here, the inversion domain boundaries can form along all the 1-1-1 planes within the cubic lattice. And here you can see when the beam, when you look into the lattice, you see two of those planes. And when you, okay, so these are two planes that when you look into the lattice, but now what is this? So these elongations are a result of the other plane that lies below and has this angle to these, and they all three of these form a prism. And so the Europium is situated in all those three planes that form this triangular prism. So we did also some magnetic measurements, and what we found is that all the wires show a magnetic susceptibility. You can see that here. And only a few of them were found to have a DC signal, and which are, we cannot interpret, we cannot say if there are paramagnetic state, antiferromagnetic, or ferro or noisy ferromagnetic. And because we are the lady in Bar Ilan who is doing the squid measurements does not have a high enough resolution. From the published data on the bulk crystals of europium, indium-2, arsenic-2, we know that the intra-layer gives ferromagnetic signals behavior, and the interlayer europium provides a antiferromagnetic behavior. So this is still something that is the main topic of our studies. Now we study more what happens on the Woodside side, and we find there are very, very interesting stuff that I cannot talk about yet, but some other time later on. And these are the collaborators, previous postdocs, and some of the work, the growth on the tilted growth was done with collaboration with the group in Copenhagen headed by Peter Krogstad, and the microscopy unit, and the group doing the squid measurements, and the theoretical group in Poland, and Chaim Weidenkopf, who I'm collaborating with, and he's doing STM. So I'll leave you with this stunning image.
Question?
I need to give you this.
I have a small question. So normally when you grow thin layers in gallium on 111A in MBE, you cannot grow very nicely thin layers. But here it grows very nice. Is it the Woodside Zinglender story?
The wires grow only Woodside.
Yes.
Yes.
That's why you cannot grow.
Yes.
Okay.
Thank you so much.
Announce that, right?
Yeah.
כמה לקח לי זמן? יותר מדי או מדי? אני גם לא שמתי.
That's right. I will give it.
It's not so important.
You can have even two.
Ah, you know, before the.
Somebody's going to get.
And that was none, you know.
It's on the
Switch
light.
on the light. The clock's on just now.
Right. We get to WhatsApp, you send the photos. It's a cool. WhatsApp.
In the email, the group call is participant.
No, create one.
Yeah, that's that.
It's the organized.
Because he has the WhatsApp number for. I hope somebody is after the tea session. You know what I say? I think.
I wanted to erase my, yeah, I got that one. I wanted to erase the talk.
So after the break, next meeting will be started.
Delete.
Yeah. This one.
I don't see.
Delete it.
Ah, you did?
Yeah.
You did?
Yes.
That's very good.
Yeah. I did insert.
Can I copy question?
Yes.
Yeah, okay. May I know the file? This is the file?
Yes, I inserted.
May I know who this pendrive?
It's mine.
Yours?
This is for the Bluetooth. This is the pen.
Oh, sorry.
Yeah.
Give it to me. This one, right? Large London Marks.
Yes.
This meeting going on? I think they stopped the meeting.
Yeah.
Yeah. Okay. I will check with him and let you know. And
Okay. Maybe we can wait for 5 more minutes and have people join in with the team and start the presentation. Yeah, you can use mine. Oh, maybe you can use
אתה תראה מה קרה לו בגלל שזה הכל כאילו שלו. תראה. זה בגלל שאני אומרת כמו... הקולגה שלנו עם המיקרוסקופיה הייתה אמור לטוס, עכשיו כותבת את התאונה שלי, אולי לא תטוס. כאילו אם אני הייתי דוחה ביום, אז אולי לא הייתי מגיעה. נזכרתי שזה הוונילה ושאני מאוד אוהבת.
Okay. So I think, yeah, with the tea, we can listen to a talk maybe. So I would be talking about decomposition of anomalous diffusion or in generalized Levy walks into its constitutive effects. I know that these are big words and this talk is quite different from the ones that I have attended today. I know that it has been an overwhelming day with so many research talks, so I would keep it light. First, I will talk something about myself. I'm currently a postdoctoral research associate at the University of Illinois Urbana-Champaign in the Department of Physics. Today's work has already been published in the New Journal of Physics, and it was a part of my PhD. It was done in collaboration with a group from Max Planck Institute of Complex Systems in Germany. So something about me, I started from India, where I did my bachelor's in engineering physics. Then I moved to the United States, mainly in Texas. So the star is a little to the south of USA, where I did my PhD. And then I moved to University of Illinois. Illinois is Midwest, very cold. It might be snowing there. So yeah, the last star is where I am currently. And now let's see where we go after this. But moving on to my presentation, before I do my presentation acknowledgements, my advisor, Professor Kevin Basler from University of Houston, Texas. Then I have Professor Holger Kans from the group at Max Planck Institute of Complex Systems, and two of members of his group, Philip Mayer, which was his graduate student back then, and Erez Agion, who was the postdoc at Max Planck Institute. We worked together on the project that I would be presenting today. So the outline would be, so the motivation is, why do I want to know about this? Because everything around us is related to data. It's data-driven innovation, and that's what we are moving towards. So, and then what is this big word that I just said in my slide, which is anomalous diffusion? What is Hurst exponent and these complex words that we would talk about later? What is a generalized Levy walk and how it all connects and the generality? So motivation, what is anomalous diffusion? I know a lot of people have heard about the normal word diffusion, but not a lot of people know about anomalous diffusion. So this is an example which we've seen and which we've also seen in so many talks, that you want to have, you take medicine, you want the medicine to go in the bloodstream or vaccine. So basically anything that we eat, like anything that we eat goes into our bloodstream and it gets diffused in the molecule cells in the small intestine where the digestion happens. So diffusion is something which is happening around us. But what is anomalous diffusion? So anomalous diffusion is also actually happening. So this diffusion over here is not normal, but it is anomalous. And so anomalous diffusion is widely observed in ultra-cold atoms and optical lattices, in molecules diffusing inside cells, which I just showed you, and intraday financial markets. So this aspect is something which is very interesting. And my advisor actually worked on this, but my presentation would be a new application for it. Now, why am I interested? Why do we want to know about anomalous diffusion? Is because since we see this everywhere, we need to know the basic cause of it, or maybe the exact root cause of why we should know about this, so that it can actually help us in something which we call as predictive modeling. So giving a background on what Levy walk is, since I talked about generalized Levy walk, so I just randomly simulated some data to differentiate between Brownian motion. A very simple example that we get in physics classes is that a drunkard's walk is actually a Brownian motion. And then what is Levy walk? So drunkard's walk is that it can walk in any direction at any point of time, and the increments that are there is also different. But how about what a Levy walk is? So the time is different, but the increments that you take in that time is basically governed by a few parameters, and we would be changing those parameters to see how we observe anomalous diffusion. So a little background on how do we come up with the word Hurst exponent again here. So I am considering a stochastic process, which is given by this equation where delta is basically the increment. So you move with these increments for a total time t. And if I try to calculate the mean square displacement, then it would linearly scale. So if we have 2h, if I put h equals half, then where h is actually the Hurst exponent, and if I put h equals half, then if I want to draw a graph between x and t, it would be a linear line. And if it is a linear line, it is called as normal diffusion. But how about this h is not equals half? That leads to anomalous diffusion. So what causes anomalous diffusion? So in statistical physics, since that was my main area of research during my PhD, is the central limit theorem. So if you know, a central limit theorem is when the increments are equally distributed, they have finite variance, and they are independent. And if we exploit all three of these, we get three effects. And if we merge all three effects, that leads to the Hurst exponent, which I showed you on the previous slide. And that is a law which my professor with few of his colleagues came up with. But let's go on to the three effects. So the first is, let's take the bottom-up approach. Let's go from the down. So if the increments are correlated, long time correlation. So when we say that the increments are independent, by saying increments are independent, I mean that if A is going up, B also goes up. That is positively correlated increments. A goes up, B goes down, which is negatively correlated increments. If A is independent of B, that means there are no correlations whatsoever. And so if it violates, it leads to something which is called as the Joseph effect. J is the Joseph exponent. And if it is not equals half, which means that there are long-time correlations. The second one is the increments have finite variance. So if everybody, like if you normally you might have seen a graph, which is like a bell curve, that's a Gaussian curve. But how about if we see an exponential graph? So in an exponential graph has a fat tail. So if you have a fat tail, which means that we have infinite variance, which means that L, which is the latent exponent, is actually not equals half, which also leads to anomalous diffusion. And the last one is the Moses effect, which is not talked about that much because it is a fairly new effect, which is actually related to the non-stationarity. By just simple words, stationary means that it is standing at a place, it is not moving with time. But non-stationary, I mean that it is moving with time. So if it is moving with time, which means that my increment distribution is time dependent. So each of these effects, or just a combination of these effects, can lead to anomalous diffusion. And how did we measure these exponents? So basically we take x equals 0, which is, sorry. So I have this equation, which I just showed you. So I calculate x of t, y of t, z of t. And then I calculate the latent exponent and the Moses exponent using, so this is the median. These are just all numerical calculations. I simulate my data. I have, these simulations are for 10 to the power 8 realizations. Since it is statistical physics, and in order to have exact calculations, we need to have a large data set. And so it is for 10 to the power 8 realizations and up to 10 to the power 5 time steps, which I will show you in graphs in the presentation. But these are also derived with the same realization. So I calculate x of t, y of t, and z of t. And if I take the median of z of t, I would get Lm. I will get this equation. I calculate my of t. So I calculate what m is. I substitute back m here, and then I get the L latent exponent. How do I calculate the Joseph exponent? I calculate the range and the standard deviation of the same stochastic process, and it would scale as t to the power j, where j would be my Joseph exponent. And by calculating the width of x of t, I can calculate the Hurst exponent. And all of these exponents are related to one another, where h is the Hurst exponent, L is the latent exponent, which tells us about the finite variance of the probability distribution. M is the non-stationary increments or the Moses effect, and J is the Joseph exponent, which talks about correlation. So if I'm given a data set, I don't know anything about it. I can use all of these equations and calculate how it is changing with time, and calculate L, M, and J, and then see, okay, if I'm getting L not equals half, or M not equals half, and J not equals half, which means that I see anomalous diffusion, and then I can maybe use it for predictive modeling and see, like, for example, a lot of people have used such methodologies to predict what would be the temperature next day. It is not, obviously, it's so hard. Like, we have apps like AccuWeather, Apple Weather. I don't think so they can predict it is going to rain the next minute because they are not accurate. Neither am I saying, can I predict it? I can't predict it either, but we need some systems which can involve accurate data modeling. And so this is just a step towards that. So now we come on to generalized Levy walks. So I consider a model of Levy-Walk. I start at x equals 0, t equals 0. I move with equal probability in either direction. So plus means positive, right direction, and minus means the left direction. I keep a constant velocity for simple purposes. Then I move at a random duration tau1. And so if I take an extra step, say that if I take an extra at t prime equals tau1, and I take another t, which is tau2, then the total time would be tau1 plus tau2. It would make more sense here. So how do I generate tau, the taus, which is the random durations? I take this equation, and using this equation, I vary the parameter gamma between 0 and 1, and I get a lot of taus. And using those taus and keeping my velocity as +1 or -1, I calculate the distance. Simple. Displacement is equal to velocity times time. And once I have the velocity and time, I can calculate the total displacement. And this is just a graph of x versus t, that I start from x equals 0, I keep on moving, and then I do the calculation at t equals t. I can go on, but I just do the calculation at t equals t. And once I do the calculation, so this is something, this is too many equations. But then since we are talking about velocity here, we need to have a probability distribution function for that. So we did not derive it, but it was already in the paper. And we actually just used the equations for the instantaneous velocity. Why do we need to care about instantaneous velocity? Is because since my probability distribution would include velocity and time, I need to know how the velocity is varying with two parameters in general. Over here, we can see gamma and mu. So if I change these two parameters, I would actually observe various regions. So I am keeping gamma as 0.5. I'm keeping tau naught because I need to have an initial time after which I can generate the times that I need for the probability distribution. And as I told you before, that I did 10 to the power 8 realizations. And so by keeping nu equals 0.375, and then I keep on changing the nu, these are just random numbers. I did not, but I just wanted them to be equally distributed between 0 and 1. Equal might not be the right word to describe it, but yeah, to just have three numbers where I can actually see them transitioning between 0 and 1. So since I was talking about the different regions that we want, what are these colors? So the red color is for t equals 10 to the power 4, and the black color is for t equals 10 to the power 7. So I am increasing the time. And with increasing time, I am seeing that the transition point right here is actually shifting towards the left-hand side. So the transition point is actually the critical velocity. And as we keep on increasing the time, the critical velocity is shifting to 0. So V over VC would just become 0. So if VC becomes 0, it would just be infinite. So when t is increasing, I would have transition point, which is just infinite. So that is what we see here. And we thought that it was interesting to see how we change, if we go on to the previous slide, how we change gamma and mu from the probability distribution to actually see the transition. Then using all of this, we actually calculated the Moses effect and the Moses exponent. Instead of taking x of t, which was the basis for our project, we actually, for this specific Levy-Walk, we chose velocity here, which we are taking to be an analogy of the displacement, which we see here. Then we calculate the Noah exponent and we calculate the Joseph exponent, where this delta is also an increment in time. And so we actually observed anomalous diffusion like this. We did not just observe some simple thing, but we actually observed anomalous diffusion in 4 different regions. As you can see that I varied gamma from 0 to 1 and we varied nu from 0 to 1 too, but it actually went till 1.5, and over that it was an infinite region, which also was very interesting to see. But my colleagues in the group right now from my PhD advisor, they are actually working on when nu is greater than 1, what happens, because it's very interesting to see. So I have region A, B, C, and D, and for each of these regions, I calculated what H, J, M, and L would be in terms of gammas and nus, because those are the 2 parameters that we are varying. So quick summary, because I don't want to, I know that we've been waiting for so long. So what I would want to take from this presentation is that data-driven innovation is required to understand the complex adaptive systems and to help in predictive analysis. So what I just showed you is that there was anomalous decomposition where H was not equals half. So we divided it into its constitutive effects. And those constitutive effects were Joseph, Noah, and Moses effect. Joseph related to the correlated increments, Noah with the fat-tailed increments, and Moses with the non-stationary increments. And they are actually seen together in a scaling relationship. And so that's the reason why I felt that this was something that would be helpful. So I actually gained my qualitative skills from the PhD that I did. But currently, I am not working on statistical physics. I'm just using the skills that I gained from that from my PhD. But my current area of research is physics education, which I think is very interesting, because if you go and talk to anybody on the street, oh, you're doing physics, it's so great. But I feel that everybody can do physics and understand physics, and that is what I want to work towards. I am currently studying student experience and performance in introductory STEM courses and their diversity and inclusion in physics, because that's something that we actually require. And how do we go about it, since it's related to student experience and performance? So I know that performance is usually measured by grades, but that is also something which we don't consider to be like, it can be deceptive as well. Like if it was not a good day for the student, you don't get good grades, but maybe that does not define his or her performance. So we are also taking qualitative studies like surveys or interviews with students so that we can actually study their experiences and learn how they feel about physics. I am actually interested in exploring the modeling of curriculum development, implementation, and assessment. So I am also teaching at the same time as I'm teaching a lab in quantum and thermophysics, where we are trying to make the lab more engaging and interactive. So through that, we are just trying to see if we can, which is a part of the curriculum development, if we can make the labs a good portion of, instead of just being aloof from the lectures which are being taught, but just being complementing the lecture so that students can have a better experience. And since I am a woman, I also feel that we have very few women. So I am also a committee member of the Committee on the Status of Women in Physics by APS. And we also work towards studies in retention and persistence in physics so that we have more women join the field and stay in the field, because I feel that empowered women would empower women. So yeah, thank you. So if you have any questions, that's my email address. Yeah.
So Dr. Vidushi,
yes.
Now you are more towards the education.
Yes.
Right?
Yes.
Okay, that's very good. So in all this analysis, you have been using data science for analyzing those that bunch of data.
Yes, yes. That was just completely simulated. Yes.
I beg you remember that Levy statistics describes phenomena like birds, like seagulls looking for prey.
Yes.
Right?
Yes.
So it's like targeted random walk.
Yes. So the prey, like the example that you're giving, is related to levy flights, and this was levy walks. So levy walks and levy flights are different. Yeah, and exactly. When I started my research in that, I was confused too. And then we decided that we will just keep it generic. And then, but we decided no, levy flight and levy walks are two different mathematical concepts. So we just focused on levy walk. Yeah. Any more questions? Okay. Thank you, everyone. Hope you have a great day and a great day tomorrow as well. Thank you. Yeah. Thank you.
I'm welcoming Khalil.
Have you copied your? Okay.
No, just with WPS. No, I don't want.
Oh, okay, okay, fine.
Okay, ladies and gentlemen, thank you for being this patient. It's been really too long, so I'm really glad to be here around among different researchers from all around the world. So my name is Khalil Zakani. I'm a doctor in the field of cosmology from Morocco, and today I'm going to speak a little bit about this primordial aspect of black holes in gravitational waves from the early universe. So I think it would be a great idea if we just give some definitions about one of the most appealing or influential theories in the history of physics, which is the theory of relativity. Okay, so and more precisely, general relativity. So this theory proposed by Albert Einstein is in fact under the goal to describe one of the fundamental interactions of physics of the universe, which is the gravitational force. So as you can see in the first equation, so Einstein wants to describe the effect of matter on the curvature of space-time. It seems a little bit difficult to view, but we can simplify just looking the right side of the equation as several tensors that describe the curvature of space-time, which would be equivalent to what we call the energy momentum tensor that describe we call the energy pressure and of matter. Okay, so like any other equation, Einstein's equation needs to have a solution, and there exist many solutions to that were proposed, namely the Friedmann-Robinson-Walker metric. So we said metric is given by this ds squared. This metric, in fact, described the evolution and curvature of space-time. And of course, it predicted the model of lambda CDM. Okay, so what we are interested in is, of course, what we call the Schwarzschild metric that described, as he named, firstly by the black hole or the black star. So the idea behind the black star is that we see, like we all know in classical mechanics, there's a term of spherical geometry, and the other term describe what we call the even horizon of the black hole, and what we call also the Schwarzschild radius. So the black star was in fact a dark object that absorbed everything. Not even light can escape of. We can only observe the accretion disk around the black hole that that is okay far from the horizon. So in fact, the first academic paper proposed by Robert Oppenheimer and Hartley Sidler was a crucial point in the history of black holes. In fact, Oppenheimer was the first one to call a black star a black hole, and he predicted that black holes are in fact created under the gravitational collapse of stars under the influence of their own gravitational field. So as we can see in our first video, a simple visualization of the black hole formation under gravitational collapse. And we all know that in physics that gravitational collapse is in fact as a fundamental mechanism in the formation of structure in the universe. Okay, so there are several research that propose the formation of black holes, not through gravitational collapse, but rather by the collision of binary system of stars, like neutron stars, or even binary system of black holes. So in fact, what do we think of this primordial aspect of black hole? And the easy answer is Hawking radiation. So Hawking was the first physicist to describe this radiation as a released electromagnetic waves or radiation that in fact cause a reducing or reduction of primordial or black hole mass, which lead or eventually leads to the evaporation of black holes. So when we talk about the evaporation of black holes, this equation proposed by Stephen Hawking described the evaporation of black holes. But the problem here is that black holes do not evaporate quickly, but rather if the mass go higher, the time of the evaporation of black hole will get longer. So the problem here is that we cannot observe evaporation of black holes in the current observation. So physicists claim that probably there are some new kind of black holes that were created in the early universe, which could be already evaporated and emitted radiation that probably we could detect currently. So when we talk about the primordial universe, there are also what's called gravitational waves. So if you could imagine there exists some kind of primordial black holes that cause gravitational perturbation of space-time, it could be they could cause primordial gravitational waves. And there are also other sources of gravitational waves, like the phase transition of the universe or cosmic strings, etc. That occur after the Big Bang. So, of course, the first detection of gravitational waves was announced by LIGO and Virgo collaboration in 2015 and announced in 2016. So the experiment is similar to the Michelson and Morley experiment that was first proposed to declare the existence of the ether, which was solved by special relativity proposed by Einstein laser. So these gravitational waves are in fact a perturbation of space-time that could be caused by massive objects like black holes. So the possibility of, so after this discovery, several signals were detected by these collaborations. And the problem here is that the mass of this binary system of black holes cannot really physically or currently exist, because the mass of the whole galaxy is just the whole mass of binary black holes cannot really exist in our galaxy. So the possibility that the binary system of black holes detected by LIGO could be a signature of dark matter was began to be seriously considered by physicists. So when we talk about the Big Bang, we all know that the Big Bang is a theory that describes the appearance of the universe along with matter and its extension. So the first paper, a formalism, was proposed by this paper that describe what we call the inflation, which is a phase that occurs after or before inflation, before the Big Bang, and it is described by what we call a decreasing of the Hubble radius. So the Hubble radius is just, you can imagine a sphere with the radius, and all the information, the physical information that can circle around in this radius would be inside this this radius of what we call the radius of Hubble. So we know that inflation is decreasing, but at the Big Bang period, they propose that there is a non-instantaneous duration we call the reheating duration, which is described by a number of equals. So this duration describes the amount of expansion of the universe after the Big Bang. So it's like a unit of expansion. We say, for example, the reheating duration is equal to 16 to 17 epochs. So epochs that's a kind of a unit of expansion. So in our paper, we propose another phase which is really important that we cannot just neglect, which is the preheating. So the preheating phase is just a phase that where the phase transition of the universe occurred. So the phase transition occurred in this duration, in this phase. So previously, physicists did not really claim that this phase is not instantaneous, but it was instantaneous that occurred after the Big Bang, and directly reheating came after it. So the reason why now we talk a little bit about modified gravity. So here the idea is just we propose modified model of gravitation to solve some problems, like the rotation of galaxy. So to explain the rotation of galaxy, we see that this is a theoretical model and this is an experimental model. So we see that they are not the same. So we need to propose modified model of gravity to solve the problem of the rotations of galaxies, and also what we call the cosmological constant problem that describe of course the problem differs between the two energy densities of a vacuum, one proposed by Landau-Sedem model, and the other is by quantum field theory. So when we talk about general relativity, we just think about parallel transport. So if you have, for example, a flat paper and try to draw a circle, and each time try to draw a tangent vector around this circle, what we do expect in a flat paper that the vector will be oriented in the same way, but in a curvature of space-time, in a paper in a curved space-time, this is not what will happen, because the orientation of the vector will change. And this change is exactly what is described by what we call the Riemann tensor. So the Riemann tensor is a tensor that really describes the curvature of space-time, and it is the main tensor that, thanks to it, Einstein came to prove the Einstein field equation. There are alternative theories that describe gravity. For example, teleparallelism. So if we have a teleparallelism in a curvature and try to draw a parallelogram, we simply will not be able to connect the beginning vector to the vector in the end. And this term we call the Witzenbach term that also describes a new theory of gravitation. We call teleparallelism, and the other model is symmetric teleparallel gravity that was proposed recently in 2021. Of course, this is just a way. So when we propose that preheating, the phase when the universe occurred, when the phase transition of the universe occurred, so we just think of this phase as in this phase occur what we call gravitational waves, primordial gravitational waves, and we could calculate their density by this curve. So those are very simple curves, but the most important is that they just give a clear idea about the interval of gravitational, the expected gravitational waves density that could be detected, and of course that fit the observation given by the bounds of the Planck's data. Planck's data, of course, is a satellite that observes the horizon of the universe. So, of course, when we talk about satellites that detect radiation in the microwave wavelengths are the satellites that that detect the horizon of the universe. So what we can see is that these kind of pictures, so each time we make a new satellite, these pictures get higher resolution and give better data. So the important here is that after the Big Bang, matter was created and light was like in a prison of plasma of latigrous particles. So the time when helium and hydrogen particles were created and just the light just escaped the particles, like the elements, light elements, and at this time is what we can see here, this radiation. So this radiation gives us very important information about the Big Bang field. One of the other elements that we study is what we call the power spectrum of curvature. So when we talk about curvature of space-time, we could calculate its power spectrum, and of course, in a modified model of gravity, we could describe or calculate the power spectrum and give this curve that describe an exponential, no, it's an increasing behavior. So when we talk about the primordial black holes in the power spectrum, so what physicists found is that the formation of primordial black holes is somehow probabilistic. So why? Because the calculations gives the curves that has a function, Gaussian function, which is this probability density function that are often used to represent Gaussian function of a normally distributed random variable with the mathematical expectation value and the variance that we call sigma. So this is the function that describes the Gaussian behavior. And of course, we could calculate what we call the variance that we see here. Of course, and related to the previously calculated power spectrum. And finally, we just calculated the Gaussian function to calculate the probability of primordial black hole production. And we found that at a specific duration, we have a total probability which is equal to 1. Of course, here is somehow to calculate the period between inflation to the end of reality. So another 2 more slides. Here we have studied the evolution, not the formation, but the evolution of black holes. When we talk about the evolution of black holes, we talk about Hawking radiation, evaporation, and reduction of mass. So we could use a modified model of gravity called FQT, and we just calculated the evolution of the mass with respect to time, and of course also the time of the evaporation. So if we just have, so if we need somehow to fine tune the parameters to expect the range of time evaporation and the precise mass of evaporation. This time, with the evolution of or reduction of black hole mass, we have also what we call the accretion disk. We saw lately in the latest picture of black hole, we saw some kind of a shadow around the black hole, which is, of course, is a result of an accretion disk. So here we just have calculated the accretion disk mass evolution in the same modified model, and just we found that the accretion disk will simply increase as the accretion mass would, of course, increase. And finally, we found that with higher masses, initial mass Mi, also Mi is an initial mass of black hole. As we go further, the time of accretion
get slow. Thank you very much. Okay, so if nobody has a question, thank you very much.
I know mine is here. No, actually in the middle. Okay. Yeah, this one, right? Jimmy. Jimmy? Okay.
Okay, good evening, everybody. Let me thank you, every one of you, for your endurance to stay till the last. So my presentation is on this enzyme inhibition-based electrochemical biosensing of organophosphorus compounds. And we'll talk about the theory and mechanism. I am from Department of Chemical Engineering, Aligarh University, India. So, seeing the diverse nature of the audience, we'll go more on a qualitative presentation. In fact, this gathering is a group of participants of several conferences, not one. So, the presentation will include the background, introduction, overview of biosensor technology, nanomaterials in biosensors, enzyme mobilization and support, enzyme-based biosensors, enzymatic reaction mechanism, non-inhibition, inhibition kinetics of enzyme NAE, and finally conclusion. So I'll try to finish in time, though the presentation is long here. So basically, these organophosphorus compounds form a variety of pesticides. So many pesticides fall under this organophosphorus compounds, and pesticides can enter from these sources in the human body. Now, these OP pesticides have high efficacy and broad spectrum of activity. Approximately 50,000 OP pesticide poisoning cases reported every year in the United States. That must be now more. This data is, I think, 2 years back. And OP pesticides irreversibly inhibit esterase, plant and animal-based enzyme in human, animals, and insects. Now, pesticides commonly occur in food and environment. And so there is the precise detection of the pesticide is important for the preservation of living health as well as the environment. And also this covers the two important sustainable development goals of UN. That is the health and as well as clean water. Pesticide residues may enter into the food chain through air, water, and soil. They are carcinogenic and cytotoxic, and it may result into bone marrow and nerve disorders, infertility, and immunological and respiratory diseases. So that's where it has a very wide implication on the human and living health. So to meet the regulatory requirements, we need efficient and portable sensing device. The conventional method of detection of these pesticides are chromatographic methods, which are, of course, expensive, laborious, and time-consuming. And biosensors, contrary to that, is efficient, low cost, and portable. So there are, as you know, biosensors are very much used, in the human health and disease diagnosis. It has application in drug discovery, novel drugs, biomedicine, environmental monitoring, pollutants, security and defense, diagnosis, health and disease, and food safety. So what essentially the biosensor? So it's a self-contained device that integrates an immobilized biological element that can be enzyme, DNA probe, antibody that recognizes the analyte, which can be a substrate, complementary DNA antigen, and a transduction element which converts the biochemical signal resulting from the infection of the analyte with the bioreceptor into an electrochemical signal. So this schematic shows you have this analyte, it interacts with this bioreceptor. These are the various categories of bioreceptors. And then finally, the biochemical signal that is sensed by these transducers that convert into, electrical signals. Finally, that is measured by electrical device. Now, typically, an electrochemical biosensor will have this analyte, which will be, a substrate, interact with an enzyme, and then that is transmitted through the electrode, and finally, the electrical signal which is generated can be measured by amperometric or conductometric, impedometric, or voltammetric device. Now, there are a whole range of these principles of biosensor applications. So we will confine to, we have enzyme inhibition based OP biosensors, and then we will take up this electrochemical, where we'll discuss about electrochemical and amperometric measurement. So there are two most problematic aspects in developing biosensors. One is the incorporation or immobilization of bioreceptor in a suitable matrix. And the other is the monitoring and quantitating the interaction between the analyte and the receptors. So biosensor can be, classified based upon the signal transmission technique. It can be electrochemical, and also based on the immobilized biorecognition element, which can be an enzyme, whole body, antibody, and so on. Well, nanomaterials have been recently being utilized as the support for immobilizing these bioreceptors and biomolecules like enzymes, because of the unique properties of nanomaterials that have been listening all through in many presentations, which has a high surface to volume ratio, easy mobilization of biomolecules, enhanced electron transfer, high biocompatibility. And in case of amperometric biosensing, the electrode surface can be tailored with different nanomaterials for example, this screen printed carbon electrode with multi-wall carbon nanotubes and some other, many other bio nanomaterials have been used. Now this facilitates the electron transfer between the enzyme's redox center and the electrode, and that decreases the working potential of the bioelectrochemical reaction. So because of these various interesting properties of nanomaterials, they have been now increasingly employed for supporting these biomolecules. So these functions of nanomaterials in biosensing are because of these, unique characteristics. They have a good electronic conductivity. They have high electrocatalytic efficacy, biocompatibility, and optical properties. Now, these carbon nanotubes, the case of carbon nanotubes, we have used in our work. And we all know these are the cylindrical graphene sheets. And they have two types, single wall and multi-wall. They exhibit quantum confinement of electrons normal to the nanotube axis, helps transport electron over long length. It has high electrical conductivity and large surface to volume ratio. So in case of electrochemical electrode, this screen printed carbon electrodes modified with multi-wall carbon nanotubes, enhancement of electron transfer, improved sensitivity can be attained with this. Also, nanocomposites have been synthesized for enhanced electrical conductivity and biosensing. Like this figure shows the development synthesis of nanocomposite, first using a layer of electrode followed by a second compound, second nanomaterial, and to help a more oriented immobilization of enzyme on the nanocomposite. Now, in case of enzyme biosensors, here we use the biomolecule as the enzyme. The biosensing agent is the enzyme. And we all, I think, we know that enzymes are basically biomolecules that have high affinity towards corresponding substrates. And they can catalyze specific reactions or preferentially some reaction over the other. At the same time, they can suppress some reaction in comparison to other. And they are specific and selective. Now, enzyme biosensors for pesticide detection rely upon these two measurements. One is the measurement of enzyme inhibition, because some enzymes are inhibited by some substrates. Now, so basically some of the substrate can inhibit the active sites, and that can decelerate the rate of reaction. So that deceleration or decrease in the rate of reaction amounts, that is related with the concentration of that substrate as that inhibitor. And the other is direct measurement of compounds involved in the enzymatic reaction. So enzyme inhibition based application can be, these are the different methods: optical, calorimetric, fluorometric, electrochemical, and devices can be rapid test strip, microfluidic devices. So these are the different type of devices that can be developed using this enzyme inhibition. Basically, your blood glucose, these kits, they are based on this enzyme inhibition. Now, there are some challenges to these enzyme inhibition based methods. Natural enzymes They have a poor producibility. So molecular cloning techniques and recombinant protein expression for enzyme production have advantages of large-scale production, simple purification, high purity, and modification at the genetic level to obtain special features that results into improved sensitivity and reproducibility. Okay. Let's move. So these are the different electrochemical detection techniques: amperometric and potentiometric, conductometric, and impedometric. So in amperometric, basically it measures the current based upon the current flow. Potentiometric based upon potential or charge accumulation. Conductometric is based on the conductive properties of the medium between the electrodes, and impedometric is the change in the impedance. So electrochemical, these biosensors have advantages such as the low cost and relatively fast response, independent of sample turbidity and color, offers additional selectivity. That is, different electroactive molecules can be oxidized, reduced at different potential, low power requirement, and do not need expensive instrumentation. Now, immobilization. What essentially is immobilization? This is the physical localization of enzyme in a definite region while retaining their catalytic activities. There are different methods of immobilization, like adsorption, entrapment, covalent binding, cross-linking, electrostatic. There are some challenges with immobilization as well. Factors important for the efficiency of immobilized enzyme biosensors. There is a leaching of enzyme, 3D structure change, diffusion resistance, and they can be overcome by site-specific enzyme immobilization. It may have poor biocompatibility for that biomolecule, and that impairs the enzyme activity. Proper orientation of the enzyme in the immobilization enhances the electron transfer, otherwise it will, negatively affect the electron transfer, like in case of random orientation. Like in this case, as you can see, this is a proper orientation. So that will give, the optimum rate of electron transfer. Whereas on the right hand side, you can have, if you have this improper orientation, that can result into inefficient electron transfer. So that aspect is to be taken into consideration in immobilization, and this can be controlled by choosing specific immobilization techniques. So there are some challenges associated with the direct electron transfer. Superior electrical performance and lifetime. Enzyme immobilized nanomaterial should have high electron conductivity and long-lasting enzyme structure. Whether direct electron transfer possible between enzyme and nanomaterials, difficult for electron to escape from enzyme. Now this compound FAD, which is called flavin adenine dinucleotide, which is a redox active coenzyme associated with various proteins, is involved with several enzymatic reactions in metabolism. And this is one of the carrier of the electron transfer. Like in this diagram, you can see that you have the electrode and it is attached with this immobile, the nanomaterial, which has immobilized enzymes. Now the electron from the enzyme, it has to escape through this FAD channel right to the nanomaterial and then through the electrode. Okay, now we come to some experimental work that we performed. So basically, we extracted this enzyme ANAE, alpha-methyl acetate esterase, and this was extracted from this wheat flour. You know, the one of the cheapest source of this enzyme, using, and finally it was purified using aqueous two-stage system. And all kinetic assays depend on the ANAE catalyzed hydrolysis of alpha-naphthyl acetate into alpha-naphthol, which reacts with a fast blue B salt solution to give a purple colored diazonium dye, which was measured by UV spectrophotometer. And finally, we obtained, this SDS phase gel electrophoresis that gives, the purified enzyme. That band shows its molecular weight of 60 kDa, which conform to the value reported in the literature. Now this shows the reaction catalyzed by this enzyme ANAE. So this 1-naphthyl acetate in the presence of this alpha-naphthyl acetate esterase enzyme hydrolyzed to 1-naphthol and acetic acid. So we studied the kinetics of this enzyme. So first we use the simple Michaelis-Menten kinetics, as we know that a host of chemical reactions follow this Michaelis-Menten kinetics. And we calculated the, from based upon this simple reaction mechanism, E stands for the enzyme, S is the substrate, ES is the enzyme substrate complex, and P is the product. On the simple mechanism, this equation can be easily obtained, the famous equation, Michaelis-Menten equation, where the reaction velocity V is equal to the maximum reaction velocity into substrate upon Km plus A, where Km is the Michaelis-Menten constant. And that is the concentration of the substrate when the rate of reaction is half of the maximum reaction. So basically, Km also shows the substrate binding affinity. So if Km is low, it means at low concentration of the substrate, most of the active sites of enzyme are bounded by the substrate. So that this is how the Michaelis-Menten kinetics can be represented, the reaction rate as a function of substrate concentration. At low substrate concentration, it follows the first order kinetics. At high concentration, it shows the zero order kinetics. Gives me after some concentration, it separates. So there are few methods to calculate these kinetic constants of Michaelis-Menten. So we did that, and finally we obtained, these constants Vmax, the maximum velocity, and Km, the Michaelis constant, using these different methods, Michaelis-Menten, the direct equation, the hyperbolic equation, as well as the linearized form of this equation that can be used in these three different, these three different equations show the different linearized form of that Michaelis-Menten equation. And we have seen that Langmuir equation gives most accurate value of these constants. Okay, now we also studied the inhibition kinetics. So as I told you before, that some of the substrate can inhibit the enzyme. And that reduces the enzymatic activity. Okay. So now in this case, organophosphorus compounds, this is found to inhibit this enzyme, which is inhibited by this organophosphorus compounds. So the inhibition can be two types, reversible, irreversible. In case of reversible, the enzyme activity can be retrieved. It can be regained after washing, and once that inhibitor is removed, and by washing, and then you obtain, it regains the activity, original activity. But in case of irreversible inhibition, the original activity cannot be regained. So in our case, we have found that this organophosphorus compounds, they irreversibly inhibit the NA. So we have used these two pesticide, dichlorvos and methyl parathion, in our study. I have to go fast. So basically, this is the reaction mechanism, and this constant, so basically enzyme combines with the inhibitor, forms a complex, and enzyme inhibitor complex, and finally that enzyme inhibited enzyme is obtained, EI. This Kd is the dissociation constant of enzyme inhibitor complex, and Kp is the phosphorylation rate constant. And the progression of all reaction is represented by this ratio Kp upon Kd, that we call as Ki, the biomolecular reaction constant. So basically, we will use a model in terms of these constants. Let me quickly go to that. Of course, this shows some basic steps of, writing the rate constant and finally obtaining this equation. Now, this equation, this Et is the residual activity of the inhibition at time t, and E0 is the initial activity of the enzyme. So, ln Et upon E0 is equal to Kpp upon 1 plus Pd upon I, and that being constant, all these are constants, can be clubbed into one constant K apparent into T. Now, if this K apparent is an apparent phosphorylation rate constant, and T is the incubation time. So if we plot ln Et upon E0 as a function of incubation time for different concentrations of inhibitors, it should give a straight line. And slope of that straight line is basically K apparent. And K apparent is basically nothing Kp upon 1 plus Kd or I. If you just take a reciprocal of this, so you obtain this linear equation. So if you plot 1 over K apparent as a function of 1 over I, right? So from the straight line, from the slope, you have this Kd upon Kp, and from the intercept, you have Kp. So this way you can calculate this Kp and Kd. And from the ratio of this, you can calculate Ki. So we carried out the experiment for these two inhibitors, that is dichlorvos. And from these plots, this shows the K apparent. Now the different lines are for different concentration of inhibitors. And then once you plot 1 over K apparent as a function of reciprocal of the inhibitor concentration, so this straight line will give you Kp and Kd. So same experiment repeated for this methyl parathion. And finally, this table shows the value of this constant, and we compared these results with the value for this isomalathion reported in literature, and we found that dichlorowas, basically Ki value is highest for dichlorowas, right? It's a more potent, pesticide inhibitor basically compared to the other two. So now that's the end of my presentation. So from all these results that was presented here, we found that hydrolysis of one methyl and one methyl acetate by Na was best represented by Langmuir plot. From that Langmuir, from the Magnus-Menten equation plot, and the organophosphorus compounds react with Na by irreversible inhibition, and Na inhibition is best represented by molecular reaction constant Ki, and methyl parathion seems more potent inhibitor of Na than dichlorowas. And both this dichlorowas and parathion, methyl parathion, have a higher inhibition than isomalathion. So of course, the further work on this will continue. So thank you for your patience listening and your endurance to sit till the end. Thank you very much. Otherwise, I was really worried that at the end, I don't know if there'll be some audience left over here or not. So this work, we started this work in Malaysia when I was there, but later I moved to India at AMU. Thank you very much. This is my university, gate of the Victorian age. It's called Victoria Gate. Yeah. So Aligarh University, that its earlier buildings were on the model of Cambridge University of Cambridge. The founder, Sir Syed Ahmad Khan, he visited Britain at that time and collected all those, images, maps, etc. And he tried to build those buildings very similar to that. Like this is called Stretchy Hall. Now they are almost 140 years, 45 years old buildings over there. This is, of course, a gate built just 10, 15 years back. And these are some buildings from Malaysia. I was there, the International Islamic University in Kuala Lumpur. So this is the skyline of the Kuala Lumpur, as many of you must have visited. So with that, I finish that.
Thank you.
So, any questions? Thank you. Can somebody speak? Okay. I was there, I was on 11 years.
Thank you, everyone.
Anything else there?
I hope everyone enjoyed the session. So with this, we can close the day and we can meet up tomorrow for the virtual presentations. Thank you.
Yeah. True. Yes, I was there. In fact, before that also I was there in UEM.
Welcome.